We are approaching the nearest star system to our Sun. This is Proxima Centauri, a stellar and planetary system that also goes by the name of Alpha Centauri c. You'll understand why it's called Alpha Centauri in a moment. We are in the constellation of Centauri, only 4.2 light-years from Earth, and therefore still in our beautiful and luminous Milky Way. The luminous object you have before you is a red dwarf. These are very common in our galaxy. They represent nearly 80% of the stars in the Milky Way. The apparent magnitude of Proxima Centauri, which is equal to 11.05, does not place it in the category of the brightest stars, the most radiant stars being of first magnitude. In fact, 85% of the energy it emits is not visible to our eyes, being mainly in the infrared wavelengths. To the naked eye, its luminosity in visible light is almost 650 times less than that of our Sun. Proxima Centauri is therefore of spectral type M5, which explains why it was only discovered in 1915. With an actual diameter of 200,000 kilometers or 125,000 miles, it is 7 times smaller than the Sun, which is 1.5 times the size of Jupiter, the largest planet in our solar system. Its mass is about 12.3% of the Sun's. But Proxima Centauri has a medium density, and its density is much higher than that of the Sun. Unlike our star, which transmits its energy to the outside by radiation, Proxima Centauri transmits it by physical movements of the plasma. The interior of this star is therefore entirely convective. The helium which is produced by nuclear fusion, instead of accumulating in the center of the star, circulates inside it. This results in a convection phenomenon which generates a permanent magnetic field. This magnetic energy is extracted from the object in the form of stellar eruptions comparable to solar flares. Some of these explosions can reach incredible dimensions, corresponding to the size of the star itself, which considerably increases its total luminosity during a certain period of time. Nearly 80% of the star's surface is active, which is far beyond the activity that we know of the Sun. This is why the temperature of its corona, even outside its peaks of activity, remains higher than that of the Sun. It reaches 3.5 million degrees Celsius, or 6.3 million degrees Fahrenheit, while our Sun does not exceed 2 million degrees Celsius, or 3.6 million degrees Fahrenheit. This violent activity is nevertheless less important than many other red dwarfs can undergo, probably because of the advanced age of this star, which is estimated at several billion years. Proxima Centauri is a planetary system. The star does not evolve alone. Far from it. It is accompanied by not one, but 3 planets orbiting it. The first, Proxima Centauri b, is a telluric planet located in the habitable zone of its host, at a distance of 7 million kilometers. Its orbital period is just over 11 Earth days. Its mass, about 1.3 times that of our Earth, and its equilibrium temperature suggest that there could be water in a liquid state on its surface. But if we assume that this exoplanet has no atmosphere, which has been destroyed by repeated stellar eruptions, no form of life could be found there. The proximity of the 2 objects probably leads to a synchronous rotation, which means that this planet permanently shows the same face to its star. As a result, Proxima Centauri b could experience very high temperatures on its exposed side, hindering the presence of liquid water, while its hidden side would be extremely cold, covered mostly by ice. But what about the regions located between these two zones? Do you believe, in case of the presence of an atmosphere, that a life is possible at the level of the Terminator, this border connecting the two faces? The second planet that orbits Proxima Centauri is a cold super-Earth of the mini-Neptune type. This is Proxima Centauri c. With a mass of 5.8 times that of the Earth, it is located at about 1.5 astronomical units from its star. Its orbital period is 1900 days, or a little more than 5 Earth years. Finally, an exoplanet, whose mass is a quarter of that of the Earth, was detached in 2022. It is Proxima Centauri d, an exoplanet distant from its host by only 4 million kilometers or 2.5 million miles. Life on this planet, which orbits in only 5 days, is fatally impossible because of its proximity to the star. Furthermore, Proxima Centauri, although discovered late, was found to belong to an even larger system. In fact, it is only the third and smallest star in a triple system, Alpha Centauri, which has been known for much longer. Do you see, not far from there, these two stars which make you eye? I suggest that we get closer to these two bright stars, Alpha Centauri A and Alpha Centauri B, which form the main duo in this triple system. They are distant from their third companion by nearly 13,000 astronomical units, or 1,950 billion kilometers, or 1,200 billion miles. This distance, which is only 5% of the distance between Alpha Centauri AB and our Sun, still suggests an orbital period of Proxima Centauri between 507,000 and 613,000 years around the main duo. The distance and its low orbital velocity explain why Proxima Centauri has long been excluded from this system, to which it is nevertheless gravitationally bound. To the naked eye, this binary system, because of the proximity of its components, appears from our Earth as the brightest star in the constellation Centauri, and the third brightest in our sky, with Sirius and Canopus surpassing it. Similar to the Sun, the two stars that compose it are respectively of class G2 and K1. Alpha Centauri A, also named Rigil Cantaris, is the largest of the stellar duo, with a mass equivalent to 1.1 solar masses and a luminosity 1.519 times that of the Sun. It is a yellow dwarf that is 10% more massive than the Sun, with a radius 22% larger. In short, you are looking at the twin sister of our Sun. Alpha Centauri B, also called Ptolemy, is slightly smaller and cooler than its companion. The mass of this secondary star is 90% of that of the Sun, and its diameter only 14%. Its luminosity is barely 45% of that of the Sun. Therefore, it has a main sequence of spectral type K, which gives it this more orange color. These two stars orbit each other in 80 years. Their orbits, slightly eccentric, bring them closer to each other by 11.2 astronomical units, or about 1.68 billion kilometers, which is the distance between the Sun and Saturn. When they move away, they can be up to 35.6 astronomical units, or 5.33 billion kilometers, or 3.1 billion miles, which is equivalent to the distance between Pluto and our Sun. Astronomy enthusiasts will have to wait until May 2035 to benefit from the next pericenter in order to observe this pair in optimal conditions. Their orbital period will then have brought them closer. But our interstellar journey gives you today the possibility to observe them as never before. So let's take advantage of it to know a little more. Do you think that this star system, which is home to stars resembling our Sun, could harbor any form of life? And why wouldn't there be, in this not-so-distant land, some hot and rocky planets with a lot of water, comparable to our Earth? If you look at the near environment of Alpha Centauri A, at first sight, no planet is visible. However, a candidate exoplanet named Candidate 1 has been studied by astronomers since 2021. Distant of about 1.1 astronomical units from the star, with a revolution estimated at 1 year, it could in fact be only a dust disk, or even an artifact. On the other hand, Alpha Centauri B could have several companions, even if they have not been confirmed by the scientific community. The first, detected in 2012, would be a planet whose mass, greater than 1.1 and 2.7 times that of the Earth, qualifies it as a super-Earth. It is called Alpha Centauri BB, or Gliese 559BB. Only this candidate orbits in a non-habitable zone with respect to its host star, on a short period of 3.24 days. Distant from 0.04 astronomical units, or only 6 million kilometers, or 3.7 million miles from its star, you can imagine that no life can develop there. The very high temperatures of this planet would be able to melt lead, but recent studies have shown that Alpha Centauri BB is actually a statistical ghost. It has therefore disappeared from the list of exoplanets. The second companion, Alpha Centauri BC, is another candidate planet that seems to evolve little further than the previous one, with an orbital period of less than 20 days. Its size, 92% that of the Earth, would have made it an ideal telluric planet. But once again, its proximity to the star that hosts it makes the presence of water in a liquid state on its surface impossible. At present, it is finally near the smallest star of this triple system, Proxima Centauri, that we are most likely to discover a habitable planet, at least in part. But let's see what the next solar systems can tell us. Although more distant, they could hold some nice surprises. Let's start with Barnard's star, which is located a little further away, in the constellation of Ophiuchus, 5.9 light-years from our Sun. Despite its proximity to our solar system, its low luminosity prevents its observation without a telescope. Indeed, it is a red dwarf of spectral type M4. In other words, it is an old lady. Of an advanced age of some 10 billion years, it presents a deficiency in metal. It contains barely 25% of the amount contained by the Sun. Moreover, it has lost a lot of its rotation energy. This one is 130 days, which is relatively slow compared to the one of the Sun, which makes it in 25 days only. Much less radiant than our Sun, it is hardly more luminous than 100 full moons cumulated. Its mass, represents 17% of solar mass, and its radius 15 to 20% of the Sun's. However, this star monopolizes the sphere of scientists for various reasons. Under its calm airs, it can still show strong fits of anger, resulting in significant stellar activity. Moreover, in 1998, an intense stellar flare was observed. The temperature reached during this eruption exceeded 7,700 degrees Celsius, or 13,800 degrees Fahrenheit, more than double the temperature of the star. Barnard's star is therefore a so-called eruptive star. In addition, it is sometimes called the runaway star of Barnard. If the stars appear as fixed points in our night sky, they all move in our universe. But these movements, when compared to the scale of our human lifetimes, seem insignificant. However, Barnard's star holds a speed record. It is the fastest moving star in our Earth's sky, not following the general flow of stars around our Milky Way. To give you an idea, this star moves across our sky about one full moon width over a period of 174 years. This may seem extremely slow to you, but compared to other stars, Barnard's star feels like it is spinning through the sky, with a relative lateral speed, that is, sideways to our Sun, of 90 kilometers per second, or 55 miles per second. Its radial velocity brings it closer to our solar system at the crazy speed of 140 kilometers per second, or 85 miles per second. By the year 11,800 AD, Barnard's star should be only 3.8 light-years away from our Earth. You are probably wondering why we are visiting Barnard's star. Why are we interested in this isolated star that doesn't seem to belong to a system? In fact, Barnard's star is a small planetary system. This star, which has monopolized planet hunters for several decades, has been the subject of more than 770 observations. Astronomers saw their efforts rewarded in 2018. An exoplanet does orbit near Barnard's star. It is Barnard Star B, also known as the planet Barnard B. This rocky planet has a mass equivalent to 3.2 times that of Earth, making it a super-Earth. Distant from about 60 million kilometers or 37 million miles, twice as close to its host as the Earth is to the Sun, it revolves in 233 days. But this close distance is not enough to place it in the habitable zone of this red dwarf. The exoplanet Barnard B, compared to our Earth, receives only 2% of the energy of its star. It evolves just beyond what is called the ice line. Its surface temperature is so cold, approximately minus 170 degrees Celsius, or minus 274 degrees Fahrenheit, that the presence of liquid water is highly unlikely. This planet cannot support any form of life. Too bad. This discovery, which is the result of an important collaboration between many scientists from all over the world, follows 20 years of studies performed with 7 different instruments. However, other candidate planets are being studied in this stellar region, including Barnard Star C and Barnard Star D. But so far, no study has been able to confirm their presence. Astronomers now know that they are likely to discover many other planets of this type near red dwarfs, especially as technologies continue to progress. The only thing left to do now is to find an exoplanet that has the right conditions to support life. Let's continue our interstellar journey and reach the binary system Luhman 16, which is only 6.5 light-years away from our Sun. Composed of 2 brown dwarfs, it is located in the southern constellation of the Sails. To date, it is the closest known pair of brown dwarfs to our solar system. Their recent discovery, which dates back only to 2013, was the result of a 13-month mission by NASA's WISE spacecraft. It acquired about 1.8 million images of asteroids, stars, and galaxies. But first, what is a brown dwarf? In reality, it is an object too massive to be considered a gas giant, but not massive enough to be a star, being unable to trigger nuclear fusion at its center. Brown dwarfs are sometimes compared to failed stars. The main component of this binary system is of spectral type L8. The second, even less bright, is also a late bloomer that appears closer to the transition threshold. These 2 objects, which are separated by more than 3 astronomical units, orbit each other in about 25 years. This slowness is explained by their low mass, although it represents about 30 times that of Jupiter. Like Jupiter, the 2 brown dwarfs are subject to strong winds, as evidenced by the bright stripes running parallel to their respective equators. If you take a closer look at Object B, you will see a complex structure of irregular clouds on its surface, sometimes light, sometimes dark. Composed of iron droplets and other minerals, these disparate clouds present extreme weather conditions, with temperatures exceeding 1,000 degrees Celsius or 1,832 degrees Fahrenheit. But let's be careful and keep our distance from this molten iron rain. Because of their low luminosity, these 2 red dwarfs offer scientists an open-air laboratory that should allow them to study this type of object more easily. Brown dwarfs could reveal the secrets that govern planetary evolution, but also the formation of stars. They could even allow the discovery of exoplanets. While brown dwarfs are not massive enough to allow hydrogen fusion like stars do, they do cool slowly as they contract, and their surface gravity increases. As a result, the surface temperature of a brown dwarf can vary considerably. It can reach degrees almost comparable to those of a star, and on the contrary, degrees as low as those of a cold planet. Their age and their physical composition are as many parameters that make them different from each other. They can then present great diversity of colors and spectral characteristics. Slight perturbations are observable in the orbits of these 2 brown dwarfs. A planet is probably at the origin of these variations. But to find this unconfirmed object, we must know on which side to look, and at what distance. Because as we have already seen, even at very large distances from each other, objects can be linked. Let's go now to the constellation of Hydra to discover the star Y0855-0714. This star is 7.2 light-years away from our Sun. This short distance on the cosmic scale makes it the 4th closest star to our Sun. Its physical characteristics place it in the category of sub-brown dwarfs, or brown dwarfs of planetary mass, its mass corresponding to 1% of the solar mass. Its formation, identical to that of stars or brown dwarfs, is the result of the collapse of a gas cloud. Only its mass, which is 10 masses of Jupiter, remains lower than the 13 masses allowing it to generate the thermonuclear fusion of deuterium, so that it can claim the status of star. If this type of object is often classified in the category of brown dwarfs of planetary mass, some scientists consider them as planets floating freely in the cosmos. Y0855-0714 is even cataloged by some as a rogue planet, especially since it seems to evolve alone, without any companion at its side. Its discovery, made possible by WISE, NASA's Wide Field Infrared Explorer, dates back to 2014. This star, whose radius is slightly smaller than Jupiter's, has average temperatures worthy of the North Pole, from about -48 degrees Celsius to -13 degrees Celsius, or between -54 degrees Fahrenheit and 9 degrees Fahrenheit. Colder than Earth's average temperatures, but warmer than those on the surface of Jupiter. Therefore, among all its fellows in interstellar space, it is the coldest object of all. But this is not what surprised astronomers the most when they observed it. Let's get a little closer to this failing star. Its spectral type Y allows us to observe its surface more closely, without the need to protect our eyes. We can admire in an atmosphere tinted with azure shades, clouds similar to those surrounding our beautiful blue planet. Isn't it extraordinary? These clouds are composed of water ice crystals and sodium sulfide. This is a first for scientists. If water vapor has already been detected in the atmospheres of exoplanets, this is the first time that water clouds are observed outside our solar system. Even at the closest to our planet, these observations are generally only possible on Earth or Mars. The giant planets are so cold that the ammonia ice clouds mask the water clouds, as on Jupiter and Saturn, and the atmospheres of Neptune and Uranus prevent any visibility. All in all, this so-called failing star is of great interest to the scientific community, especially since it evolves alone in interstellar space. As you have probably noticed, no other object seems to be gravitationally linked to this failed star. Observations looking at it therefore cannot be subject to interference from a nearby star that could cause any glare. Let's now turn our attention to another star system, also located a short distance from our solar system. Let's go to the constellation Leo, where a red dwarf has, like our Sun, a corona. Here we are approaching Wolf 359, a star that is certainly quite pale, with a spectral type of class M6.5, but which hosts 2 exoplanets. They are respectively named Wolf 359b and Wolf 359c. Wolf 359 is one of the smallest stars known to date, its mass of 0.09 solar masses being at the lower limit. Indeed, a star whose mass is lower than 0.08 solar mass is not massive enough to ignite the hydrogen of its core. Wolf 359 is then at the limit to be considered also as a brown dwarf. Because of its small size, its radius being only 0.16 solar radius, it is entirely convective. The helium produced in its center arrives at its surface thanks to the movement of the plasma. Because of this weak and slow production of energy, it will probably remain in this state much longer than our Sun, which burns its cartridges at high speed. The life of the latter is estimated at 10 billion years, and we know that it has reached 4.55 billion years. In place of our Sun, the faintness of Wolf 359 would represent about 10 times the brightness of our full moon. Not enough to cause us the slightest sunburn, even worse, not enough to hope for any presence of life on our planet, which would then be covered with ice. However, this young spinner at least 100 million years old, and whose projected rotation speed is less than 3 kilometers per second, or 2 miles per second, is a flare star. In other words, a variable star. Of UV Ceti type, it undergoes sometimes brutal increases of its luminosity on all its spectrum. Its magnetic activity induces brief eruptions which can occur at a rate of 32 events over a period of 2 hours, most of them being microeruptions. Its surface temperature, much lower than that of our Sun, is nevertheless 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. This temperature is low enough for the chemical compounds to remain long enough to be observed with their spectral lines. In 2001, molecular lines composed of carbon monoxide, iron hydride, chromium hydride, water, magnesium hydride, vanadium oxide, or titanium oxide could be observed for the first time from a terrestrial telescope. Apart from the Sun, Wolf 359 is therefore the first star to expose the spectrum of its corona to the light. The study of its spectrum revealed the absence of lithium lines. This element has probably been entirely consumed by fusion in the core. This is the parameter that allows us to conclude that this star must be at least 100 million years old. As we have seen, Wolf 359 is not alone. It has 2 companions. 2 planets orbit around it. The first, Wolf 359b, is 276 million kilometers, or 170 million miles away, and the second, Wolf 359c, is close to 2.7 million kilometers, or 1.7 million miles. The more distant of the two has a mass of about 43.9 Earth masses and orbits Wolf 359 over a period of 2,938 days. The closer one, Wolf 359c, is much less massive, with its 3.8 Earth masses. It orbits its star in 2.7 days. Unfortunately, these 2 planets are either too far away or too close to their host to be located in the habitable zone, which extends from 3.6 and 7.7 million kilometers away, or between 2.2 and 4.7 million miles. Wolf 359b would be so cold that it could only be covered by a thick coat of ice, while its companion, Wolf 359c, would suffer from temperatures too high for water to remain in liquid state on its surface. Our efforts to find a potentially habitable exoplanet will therefore have to focus on another star system. Another red dwarf, located in the Big Dipper constellation and 8.3 light-years away from our Sun, is particularly promising. Let's join the second Argelander star, better known as Gliese 411, or Lalande 21185, an old lady between 5 and 10 billion years old. This red dwarf of type MV5 is cold and dark. Its luminosity, which is 6,000 times lower than that of our Sun, does not prevent it, however, from being among the brightest red dwarfs in the solar neighborhood. Its apparent magnitude is only 7.47, so it cannot be observed with the naked eye. It has all the characteristics of a half-sun, a mass of about 46% of solar mass, and a diameter equivalent to 40% of that of the Sun. If its mass had reached 50% of solar mass, it would probably have entered the category of red giants. Its surface temperature, which is about 3,328 degrees Celsius, or 6,022 degrees Fahrenheit, or 62% of that of the Sun, can undergo sudden variations as well as its luminosity. Indeed, Gliese 411 is a so-called eruptive star, a flare. The eruptions on its surface are as unpredictable as they are spectacular, especially since the excess luminosity produced contrasts with the usual pallor of the star. At first sight, apart from its spectral anger, this star has nothing extraordinary. However, it integrates the list of interesting objects for exoplanet hunters. On the one hand, because of its proximity to our Earth, and on the other hand, because of its constant radial velocity. It is a perfect example of the stability level of red dwarfs, although it moves perpendicular to the galactic plane at high speed with an average of 47 kilometers per second, or 30 miles per second. In its interstellar course, Gliese 411 undergoes, however, astrometric perturbations. The study of these variations has established that this red dwarf is indeed part of a multiple system. Since 1996, it is known that not one, but two, or even potentially three planets are in orbit around Gliese 411, which is therefore the fourth closest planetary system to our Sun, after Alpha Centauri, Barnard's star, and Wolf 359. The first planet is called Gliese 411b. It is a super-Earth. Its mass corresponds to 3 Earth masses. Very close to its star, at 0.08 times the distance Earth to Sun, it completes its orbital period, which is very circular, in only 13 days. Gliese 411b is 5 times closer to its host than Mercury is to the Sun, and although this star is less hot than the Sun, the planet is not in the habitable zone. It receives 3.5 times more energy than the Earth receives from the Sun, and must therefore have strong similarities with Venus. A second planet evolves at a little less than 3 astronomical units from the mother star. This is Gliese 411c. This exoplanet, whose mass exceeds 13 terrestrial masses, covers its orbit in 2,946 days. It is therefore a Neptune-like planet, located well beyond the habitable zone. Finally, a third planet could also interfere with the main star, placing it in the category of quadruple systems. Named Gliese 411d, it is 0.5 astronomical units away from its host. With a mass equivalent to 4 Earth masses, it has an orbital period of 215 days. It remains to be seen if its temperature and atmosphere are suitable or not for any form of life. What about you? What do you think about it? But let's leave this question aside for the moment. A star sparkling like no other attracts your attention, and for good reason. You are looking at Sirius, the brightest star after the Sun in our winter sky. You know, the one that flashes in the sky, reminding you of the intermittent lights of a plane at high altitude. Moreover, its name, which was not chosen at random, means bright in Greek. We find traces of its sparkling presence since the dawn of time. For the ancient Egyptians, the Nile star, as they called it, announced the periods of flooding of the river. In Chinese astronomy, it was called the celestial wolf, while the Greeks associated it with the dog of Orion, then called Sirius. This star also played a fundamental role for Polynesian navigators by serving as a landmark. The stars were their only reliable tool for orientation at sea, and Sirius, easily recognizable, marked the zenith of the most honored place of worship in the entire Polynesian region. It is located in the constellation of the Great Dog at a distance of 8.6 light-years from our own system. That is why it is also known as Alpha Canis Majoris, being the brightest star in this constellation. Its apparent magnitude is -1.46. To be clear, this negative number means that Sirius is brighter than our Sun, a magnitude of 1 being equivalent to the solar luminosity. This is why, despite a distant, but at the same time so close to our solar system on the scale of the cosmos, Sirius, which is classified in the category of white stars, appears so bright. Its brightness is punctuated by variation when observed from Earth. As you can see, however, it does not blink any more than our Sun. This effect is due to the fact that Sirius is located very low on our Earth's horizon. The light emitted by the star must therefore cross a large part of the atmosphere before reaching us. It is therefore more or less masked by the turbulence of the environment that separates us from it, hence its flickering. During our approach, if you look carefully at Sirius, you see that it is in fact a binary star. It is composed of two stars. The main one, Sirius A, is a white, slightly bluish star of spectral type A0 or A1. More luminous than our own star, it is 2.3 times more massive and 1.8 times larger than our Sun. I let you imagine the heat that reigns on its surface, its temperature being higher than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. That is to say, much more than our Sun, which burns at 5,504 degrees Celsius, or 9,930 degrees Fahrenheit. All these characteristics evoke the relatively young age of Sirius, which should not have more than 200, even 250 million years. It has for companion a white dwarf named Sirius B. The latter, because of its small size, its proximity to Sirius A, and its low magnitude of only 8, was discovered only very late in 1862. As a white dwarf, Sirius B has a size comparable to that of the Earth, while its mass is equivalent to that of the Sun, and its estimated temperatures are 3 times higher than those of Sirius A. Separated from the main star by an average of 19.5 astronomical units, or 19.5 times the distance between the Earth and the Sun, it orbits around it over a period of 50 years. Because of a strongly marked elliptical orbit, the distance between these two stars can vary from 8.1 to 31.5 astronomical units. This maximum distance will soon be reached by 2024 to 2025, while the next passage at the periastron of the system, i.e. the moment when the two stars will be the closest, is planned for 2044. This binary system is waving alone in the cosmos. No planet has yet been seen in its vicinity. Sirius being a young star, it is unlikely that exoplanets are in orbit around it. However, since 2018, NASA has been exploring this bright object with the Transiting Exoplanet Survey satellite. And who knows, its high brightness could mask one or even several planetary objects. At almost the same distance from our Sun, another stellar duo awaits us. Let's join, at 8.7 light-years from our solar system, Luyten 726-8, a binary system hosting two stars, BL Ceti and UV Ceti. They are once again two M-type red dwarfs, probably younger than our solar system. With a low luminosity, they are not visible to the naked eye. This is why they were only discovered in 1948. These two stars, like twin sisters, have many similarities. Both have almost identical masses, radii and luminosities. Their mass is 10% of the solar mass, their radius 14%, and their combined luminosity is 11,000 times less than that of the Sun. It is therefore not surprising that we detect an identical temperature on the surface of these two stars, which is close to 2,330 degrees Celsius, or 4,220 degrees Fahrenheit. If the two stars orbit around a common barycenter over a period of 26.5 years, their orbits are marked by a strong eccentricity. The distance between them can therefore vary between 2.1 and 8.8 astronomical units, causing strong tidal forces between the two objects. BL Ceti, the main component of this duo, has a luminosity 6,000 times lower than the Sun, while the secondary star, UV Ceti, has a luminosity 4,000 times lower. UV Ceti is the better known of the two. The latter rotates very fast, with a rotation of only 0.2 days. Its rotation speed feeds a powerful magnetic field, where bubbles, charged with matter by the convection currents typical of red dwarfs, trigger important eruptions. UV Ceti is therefore a flaming star. During one of its numerous eruptions, its luminosity can be multiplied by 100 in a few seconds. At the same time, massive emissions of UV and X-rays ignite the star's environment. In 1952, the observation of UV Ceti allowed to count not less than 75 variations of its luminosity in only 20 seconds. This particularity places it in the category of variable stars, where, moreover, it serves as a reference. Indeed, other eruptive stars are sometimes included in the category of UV Ceti variables. The main star is less active. This is probably related to the fact that it has a lower rotation speed. Nevertheless, the motions of these two stars are at the origin of unusual stellar winds. Their surfaces are subjected to winds more violent than those experienced by the Sun, although weaker at equivalent distances. The resulting heliosphere extends to 10 or 20 astronomical units. During massive eruptions, this heliosphere can be expelled up to 100 astronomical units. When the eruption of one of the two stars is directed towards the second, a shock zone is created, somewhere between the two stars, giving a complex and non-spherical shape to the heliosphere surrounding UV Ceti. In short, the environment near this star system does not seem to be the most favorable to host a planet in the best conditions. This one, in addition to being subjected to stellar winds, would inexorably undergo the unpredictable explosions of anger of UV Ceti. However, oscillations have been noticed in the orbits of the two stars, in particular that of BL Ceti. But what could a planet located in this tiny part of space look like? A hypothetical planet orbiting UV Ceti would have no atmosphere, as it would be deteriorated in a few millennia by repeated flares. On the other hand, a planet orbiting BL Ceti could keep its atmosphere for more than 100,000 years. However, the important forces of tide undergone would dress this planet of a multitude of volcanoes, where the only existing rivers would welcome only the flows of a burning lava. Moreover, the strong fluctuations of temperatures would have reason of the rock present on its surface, transforming it gradually into dust, which would mix with the volcanic ashes. A planet in orbit around these two stars would be more than 30 astronomical units away. Of course, it could contain its atmosphere, but its temperatures below minus 230 degrees Celsius or minus 382 degrees Fahrenheit would not be very attractive, and the luminosity on this planet would be null, except during strong stellar eruptions. In short, if the binary system Luyten 726-8 can be attractive by its spectacular side, it is not very welcoming. Ross 154 is the 9th closest star system to our Sun. Located in the constellation of Sagittarius, it is 9.7 light-years away. Composed of a main sequence star of spectral class M3.5V, it is not visible to the naked eye from our Earth. Ross 154 is therefore by definition a red dwarf star, cold and dark. Its discovery by Frank Elmore Ross dates back to 1925. Ross 154, also named Gliese 729, has a mass equivalent to 17% of solar mass. Its size is about 20% of the Sun. Its apparent magnitude is only 10.44. The luminosity of this star is relatively low and represents only 0.4% of the Sun. Ross 154 is so small that it is not able to expel heat from the core at its surface, as do the larger red dwarfs. So it carries this heat to its surface by convection. Moreover, as you can imagine, the heat at its surface is much lower than that of our Sun. It is estimated at 3,019 degrees Celsius, or 5,460 degrees Fahrenheit. However, this star is not so ordinary. Like many red dwarfs, it is an eruptive star. Moreover, it integrates the category of UV Ceti-type variables. This flare star, during prodigious eruptions, can thus generate X-ray emissions comparable to, or even superior to, those of the Sun. In addition, to integrate the catalog of eruptive stars, Ross 154 is also part of the variable stars of type BY Draconis because of its variations of 0.03 magnitude, noted on a period of 2.87 days. In addition, its relatively low metallicity, estimated at 56% of that of the Sun, as well as its moderately high rotation speed of 3.5 kilometers per second, or 4 miles per second, allow to conclude that it is a relatively young star. Ross 154 is less than 1 billion years old. No planet has been detected in its environment. In any case, as for a large part of red dwarf stars, the numerous and violent eruptions which burst out at its surface would fatally harm any form of life which could develop in its habitable zone, the planet having necessarily to be close to the star. In the constellation of Andromeda, another red dwarf has almost the same characteristics. It is Ross 248, also known as Gliese 905. Located at 10.3 light-years from our solar system, it is similarly a flaming star that sometimes increases its brightness suddenly. Its mass is about 12% of the solar mass, its diameter is 7%, and its luminosity is 11,000 times lower than the Sun's. Periods of variability have been reported. ranging from 4.2 years to 120 days, and 5 others between 60 and 291 days. What if these were astrometric disturbances that could be attributed to the presence of an invisible companion? For the moment, no planet or other object has been found orbiting this star. In any case, the meteorological vagaries of this star can only harm any form of life in its proximal periphery, if it could have developed at all, especially since its reddish color would prevent any form of terrestrial-type plant life from properly carrying out its photosynthesis process. Another star system is of great interest to the scientific community. It is an orange dwarf star that plays hide-and-seek. Let's go to discover this mysterious star in the constellation of Eridanus, 10.5 light-years from our solar system. This is Epsilon Eridani, also known as RAN. Its apparent magnitude of 3.73 makes it the third closest individual star system visible to the naked eye. Younger than our Sun, it is between 200 and 800 million years old. Being a main sequence star of spectral class K2, the energy generated in its entrails by the nuclear fusion of hydrogen is diffused at its surface, where the temperature is higher than 4,800 degrees Celsius, or 8,670 degrees Fahrenheit. This is what gives it its beautiful orange color. Slightly smaller than our Sun, its mass is 82% of the solar mass, and its radius is 74% of the Sun's. Its average period of rotation is 11.2 days. Epsilon Eridani is thus more than twice less fast than the Sun. If its luminosity is only equivalent to 34% of the Sun's, on the other hand, it generates a level of magnetic activity higher than that of the Sun. The chromosphere and the corona that surround it are therefore much more dynamic. As a proof, the average intensity of the magnetic field at its surface is 40 times higher than that of the Sun, and its stellar winds 30 times more violent. But this activity is not regular at its surface. Some regions are much more active than others. Epsilon Eridani is therefore considered as a variable BY Draconis. It is a star that has a disconcerting behavior. Sometimes it brightens, sometimes it darkens. It has cycles of 27 years during which its brightness decreases considerably over a period of about 2 years. This decrease in intensity was last seen from 2009 to 2011. What gigantic object could shadow this star so much? It is known that Epsilon is surrounded by not one, but 2 rocky asteroid belts. One, 3 astronomical units away from the star, the second, 20 astronomical units away. However, they cannot explain this particularity. In fact, Epsilon is a binary star with eclipses. This means that it is accompanied by a dark object, probably a star, or even a pair of stars, surrounded by a disk of dust, dense and thick enough to make it invisible. These 2 stars are probably 30 astronomical units apart, and the diameter of the rings surrounding this pseudo-dark star must reach 20 astronomical units, occulting the main component like a curtain. However, Epsilon still reserves us a surprise. In addition to these variations of light, a study over 20 years of its radial speed has highlighted periodic variations. This observation has allowed to highlight the presence of a giant planet of the size of Jupiter in orbit around the star. This planet, named Epsilon Eridani b, or AE-Jur, follows a slightly eccentric elliptical orbit. Its semi-major axis is equivalent to the distance between our Sun and the asteroid belt. The size of this gas giant is estimated between 80 and 160% of the size of Jupiter. It completes its orbit in 7 years. If a planet could have formed in this environment, it is probably not alone, especially since the observed dust cloud has an asymmetry that could be explained by the presence of a second planet. This one would then be located much further away than the first one and would have a much longer orbital period. I now propose you to join another red dwarf. Yes, another one. Remember, red dwarfs alone account for about 80 to 85% of the stellar population in our galaxy. But this star should be of great interest to you, as it is considered by the scientific community as the best star to search for potentially habitable exoplanets. Let's discover Gliese 887, also known as Laniakea 9352. It takes the 12th place in the list of stellar systems closest to the Sun. Located in the constellation of Southern Pisces, 10.7 light-years from our Earth, it appears to be the brightest red dwarf in our sky and requires only a small telescope to be observed. Its luminosity is about 1% of that of the Sun. It is also the most massive of all red dwarfs, with nearly half a solar mass, at a distance of 6 parsecs from the Sun, or a little less than 20 light-years. But what makes this star even more exceptional is its low photometric variability, which makes it a quiet red dwarf like no other. Unlike its companions, Gliese 887 is less magnetically active and does not seem to ignite by triggering huge explosions or stellar eruptions. In other words, if there are planets orbiting in its narrow habitable zone, we could well detect traces of life there, and even, why not, consider terraforming them when technology allows it. This is very good news. On the one hand, the inactivity of this star greatly facilitates the remote observation of any exoplanetary atmosphere. On the other hand, exoplanets orbiting Gliese 887, which have not undergone many energetic explosions, may have retained their original atmosphere. What if I were to reveal to you that at least 2 exoplanets have been identified near this star? The first, Gliese 887b, is a super-Earth of about 4 Earth masses. It orbits its star in 9.3 days. Unfortunately, the small distance between it and its host, a little over 10 million kilometers, or 6.2 million miles, means that the temperature is far too high for water to be present in a liquid state. The second, Gliese 887c, is also a super-Earth, whose mass is estimated at 7 times that of the Earth. It orbits the star in 21.8 days. Do not rejoice too quickly, because unfortunately, for it too, the conditions are not optimal for it to harbor any form of life. Although a little further away from the star than the first described super-Earth, it is only 17 million kilometers or 11 million miles away. Once again, it is too close, and therefore too hot to maintain water in a liquid state, the temperature of its atmosphere having to reach at least 70 degrees Celsius, or 158 degrees Fahrenheit. However, any hope of finding an exoplanet in the habitable zone of Gliese 887 is not abandoned. Moreover, a candidate planet has been located in the habitable zone of this planetary system. Named Gliese 887d, This super-Earth of 8 Earth masses orbits its star in 50 days. Contrary to the 2 previous planets, it could therefore experience temperate temperatures and could therefore be well suited to the development of life. Another planetary system, also a little less than 11 light-years away, is located in the zodiacal constellation of Virgo. Let us now approach Ross 128, also named Gliese 447, the 13th closest star system to our Sun. This star has an apparent magnitude of 11.13. Its luminosity is therefore 100 times too low to be observed with the naked eye from our Earth. The primary object of the system is once again a red dwarf. Its mass is 15% of the solar mass, and its radius 21% of the Sun's. The temperature of its stellar atmosphere is 2,900 degrees Celsius, or 5,252 degrees Fahrenheit. Most of the energy radiated by the star is visible only in the infrared, with a luminosity 33,000 times lower than that of the Sun. As a result, it is of spectral type M4V, hence its typical cold orange-red color. Twice as old as our Sun, this star has been shining for over 9.4 billion years. Despite an entirely convective activity and a rotation speed considered slow, this flare star seems to have a long-term stellar activity cycle. As mentioned earlier, Ross 128 is part of a system. It hosts an exoplanet. This one, probably telluric, orbits in the interior edge of the zone of habitability, and thus receives approximately 38% more sunlight than the Earth. The planet Ross 128b is therefore potentially habitable. It is, after Proxima Centauri b, the second closest exoplanet to our solar system to enter this coveted category of cosmic objects. Let's see what this satellite looks like. Slightly more massive than Proxima Centauri b, Ross 128b contains at least 1.35 times the mass of the Earth. According to its hypothetical composition, if it is composed only of pure iron, it could have a diameter equivalent to half that of our Earth. According to the opposite hypothesis, if it is only composed of hydrogen and helium, it could then measure 3 times the size of the Earth. But considering that this planet could be telluric, its radius could be 1.1 times the Earth's radius, or about 7,000 kilometers or 4,350 miles, and its mass would then be 35% more massive than that of the Earth. Depending on its atmospheric component, its surface temperature could even be approximately the same as that of our Earth. Assuming that all these parameters are green, what about those related to the orbit of this planet? Ross 128b orbits rapidly around its star, in only 9.9 Earth days. This orbit is quite circular, thus having an eccentricity of only 0.036. It is more than 20 times closer to its host than the Earth is to the Sun, at a distance of 7.4 million kilometers, or 4.6 million miles. This proximity suggests that the planet has a gravity barely greater than that which we experience on Earth. But above all, it must always present the same face to its host. Apart from this particularity, this exoplanet is the only one known to date to resemble so closely our beautiful blue planet. But we must not lose sight of the fact that red dwarfs can be angry. Although the Olympian calm star Ross 128 seems to behave peacefully, it could have eroded the atmosphere surrounding the planet, evolving next to it in the past, during massive and repeated eruptions. But if this is not the case, if this star has always been peaceful, then Ross 128b could well be enveloped by an atmosphere. Why not? Welcome it. We could even go so far as to consider that it could already be home to one or more extraterrestrial life forms. Our interstellar journey is coming to an end. It has taken you almost 11 light-years from our Sun. You have been able to approach the star systems closest to our Earth. In this infinitely large space, an invaluable quantity of other systems remains to be discovered. Among those already listed, some are located at a short distance. Others, on the other hand, are several million light-years away. If for the majority of them, many similarities can be noted, for others one can distinguish an unusual composition. This is particularly the case for a system that is 150 light-years away from our galaxy, the system HD 98800, or TV Crateris. This one consists of two pairs of stars, distant from each other by 150 million kilometers or 93 million miles. I let you imagine what our sky would look like with 4 suns. But what makes it even more spectacular is the disk of dust that surrounds one of these two pairs. Another system, well known to all, also presents singular characteristics. It is Alpha Ursae Minoris, more often called Polaris. You know this star well under its common name of Polaris, easily spotted near the North Celestial Pole. It is the brightest star in the Little Dipper constellation. It is 431 light-years away from our Sun. But did you know that this star is in fact a multiple star? Polaris, which is a supergiant Cepheid variable, has in fact 2 smaller companions. It is thus a triple system. It has also been found 2 other components, even more distant. The one who reigns supreme in this gigantic domain, and without whom the Earth, and consequently man, would be nothing, is the Sun. This giant ball of hydrogen and helium contains 99.9% of the total mass of the solar system. The Sun is a star. Although it seems huge to us, it is medium-sized with a diameter of almost 1,400,000 kilometers, or 870,000 miles. The Sun is in the middle of its life cycle, since it has already used up between 35 and 45% of its hydrogen reserves. In about 6 billion years, the hydrogen will be totally consumed, and the Sun will start to expand. It will then become a subgiant star, brighter but less hot. 1 billion years later, the star will become a red giant, growing even larger. It will then eject its outer layers into space until its core curls up into a white dwarf. It is within its core, the central region of the Sun, that nuclear reactions occur. The energy released rises to the surface and escapes in the form of light and radiation. It is thanks to this same energy that life on Earth is possible. The atmosphere acts as a shield. It allows the solar energy to penetrate and prevents the heat from escaping, while preventing the dangerous solar radiation from reaching the planet. This effect is called the greenhouse effect. The atmosphere keeps us comfortably warm day and night. Human beings are entirely dependent on the Sun, which is involved in the entire life cycle. The star heats the land, oceans, and air. When the water evaporates, clouds form. Within these clouds, water droplets are formed as the water vapor cools. They will then fall back down as rain. Humans, animals, and plants benefit from this water. Plants also use sunlight for photosynthesis. They convert carbon dioxide and water into carbohydrates necessary for their development. In return, they release the oxygen that living things need to breathe. Mercury is the closest planet to the Sun. It looks like a ball of iron surrounded by a thin rocky mantle. Its surface is, like that of the Moon, covered with impact craters. The Caloris Basin is one of the best-known impacts, so large that it could contain almost the whole of Texas. Apart from the craters and plains, compression faults appear, which form cliffs, and which can reach 3 kilometers or 2 miles in height. Having no atmosphere or liquid water, Mercury's only erosion comes from the impact of meteorites, asteroids, and comets. Mercury has no moon. Its proximity to the Sun results in an average ground temperature of 430 degrees Celsius, or 800 degrees Fahrenheit. It also experiences great temperature contrasts, since when its hemisphere is plunged into the night, the temperature decreases to about minus 200 degrees Celsius, or minus 328 degrees Fahrenheit. It is smaller than the Earth, but so dense that it certainly has an important iron core. Venus is the closest planet to Earth. It is about the same size as Earth, but is far from being its twin. A thick atmosphere of carbon dioxide covered with clouds of sulfuric acid obscures its surface. The pressure exerted on the ground is equivalent to that of a deep sea of 900 meters or 3,000 feet. While it is farther from the Sun than Mercury, the average ground temperature of Venus is warmer and reaches up to 490 degrees Celsius, or 914 degrees Fahrenheit. The surface of Venus is covered with volcanic edifices, such as pancake domes, which are circular and flattened reliefs formed by a gas-rich lava. This lava spreads like a pancake batter, then solidifies and breaks. The highest volcano on Venus is Mont Mons, which rises to 8,000 meters or 26,000 feet. Its lava flows can reach hundreds of miles and miles in length. Mars comes in fourth from the Sun. Its diameter of just over 6,700 kilometers or 4,200 miles is twice as small as Earth's. It has a thin atmosphere containing mainly carbon dioxide. Its unstable climate leads to the formation of ice caps. Many extinct volcanoes culminate on its surface, including Olympus Mons. It is one of the highest known landforms in the solar system, with a peak reaching over 21,000 meters, or 69,000 feet. It seems that liquid water, in the form of real seas, covered its surface in the distant past. The first geological hours of Mars were marked by meteoric bombardment and strong volcanism. The ancient craters thus eroded by water gave birth to rivers. There was then at that time a hydrodynamic cycle. The climate should be mild and stable, thanks to the presence of oceans allowing the water cycle. Nevertheless, the weak mass of the planet could not allow to retain the gases of its atmosphere, and the cycle of the water dissipated. The water would then have evaporated and been absorbed within porous rocks. The density of Mars is lower than that of the Earth, because its smaller mass compresses its deep layers less. It is called a red planet because of a thin layer of red dust composed of iron oxide, that covers its surface. Most of the southern hemisphere is covered by high plateaus riddled with impact craters. In the north, there are basins and large volcanoes. Mars has 2 moons, Phobos and Deimos. These are asteroids that have been captured by its gravity field. They are riddled with craters and have irregular shapes. Both are small, with modest diameters of 27 kilometers or 17 miles for Phobos and 15 kilometers or 9 miles for Deimos. The distance between Deimos and Mars is such that it is in synchronous orbit with the planet. The Moon is always at the vertical of the same place. A cluster of asteroids circulates between the orbits of Mars and Jupiter. Irregularly shaped, they can reach sizes ranging from a small stone to a mini planet. The largest of them, Ceres, has a diameter of about 950 kilometers or 590 miles. It was even classified as a dwarf planet. Asteroids are composed of minerals, metal, or carbon. They are riddled with impact craters. They could not aggregate to form a planet because the gravity field of Jupiter disrupted and scattered the blocks. These rocky bodies orbit the Sun, but their small size prevents them from being classified as planets. The majority of asteroids are located in the main belt. Its thickness measures between 100 and 300 million kilometers, or between 60 and 190 million miles. Asteroids are classified into 3 distinct families according to their chemical composition and morphological characteristics. We find the asteroids of type C, called carbonaceous, the asteroids of type S, rich in silica, and the asteroids of type M, said metallic. About 75% of them are C-type asteroids. They are lodged in the most distant regions of the asteroid belt and are the least luminous. Can these lumps floating in the sky be made to crash into the Earth and become a threat to life? Some fragments of asteroids can head towards the Earth and collide with it. They are called meteoroids. If one of these meteoroids enters the Earth's atmosphere at high speed, the friction creates heat so great that it burns the meteoroid to ashes and produces a trail of light across the sky. If the meteoroid does not burn up completely, the remaining piece can then touch the Earth. It is then called a meteorite. An impact with a large meteorite could obviously leave obvious signs on the surface of the Earth and cause dramatic consequences for life. Jupiter is the largest planet in the solar system. It could contain all the other planets in its interior. Its composition is almost entirely gaseous and consists mainly of hydrogen and helium. Jupiter is more like a star than a real planet. After Venus, Jupiter is the most luminous planet. It has a compact core of rock and ice, formed of compressed hydrogen and helium. This core represents about 5% of its mass. It is enveloped by volatile elements. Jupiter is spectacular. It has no solid surface and a dynamic atmosphere. From the Earth, we can observe an alternation of dark belts and clear areas. This banded arrangement is due to its rapid rotation, which stretches the disturbances around the globe and confines the clouds of its atmosphere in a set of parallel lines. In the middle of these bands, cyclones and anticyclones are present. The most famous of them is the Great Red Spot. It owes its bright color to molecules containing phosphorus. This anticyclone is larger than the Earth. The Great Red Spot is constantly shrinking, from 40,000 kilometers or 25,000 miles, in 1930 to 16,000 kilometers, or 10,000 miles long, in 2014, and would disappear within 70 years. Jupiter has a ring system that remains dark and is only visible when it is in the planet's shadow. The planet is not only distinguished by its size, it also has the largest number of moons. To date, 95 are known. Saturn is the second largest planet in the solar system, but what makes it famous are the rings that surround it. With the help of a small amateur telescope, it is possible to observe them from Earth. Saturn's rings are a world apart. They are composed of many ice particles acting as an independent satellite. Some of them can reach the size of a house. The particles in these rings are shiny, coated, or composed of highly reflective ice. Saturn's rings are brighter than those of other planets and reflect up to 60% of sunlight. They are flattened. Although they measure 280,000 kilometers or 170,000 miles in diameter, their thickness does not exceed a few meters or feet on average. Saturn has a solid core of rock and ice. Its atmosphere contains mainly hydrogen and helium. The clouds are deeply buried, and their color, blurred by layers of haze, gives the planet a livid hue. One of the characteristics of Saturn is that it has a flattened shape at the pole. This is due to its extremely fast rotation on itself, of less than 10 hours 30 for a complete turn. Saturn, imposing in terms of mass and gravity field, has captured a large number of asteroids that have become its moons. 83 known satellites are attributed to it today. Among them, Titan has a diameter of more than 5,000 kilometers, or 3,100 miles, and is the second largest moon in the solar system. Titan is surrounded by a thick layer of nitrogen. Being quite far from the Sun, the temperature on its surface is extremely low. By continuing to move away from the Sun, we can observe in the sky a ball with blue-green reflections. It is the planet Uranus. It is the third largest planet. Its diameter is 4 times that of the Earth. Its particular color is due to the presence of methane. No details of its atmosphere are visible, neither cloud bands nor cyclonic formations. Unlike Jupiter and Saturn, which are considered as gas giants, Uranus is similar to an ice giant. It is much denser, and its internal layers must contain elements heavier than hydrogen, like ice. Uranus goes around the Sun in a little more than 84 years. This situation gives it strange seasons. This is also explained by the fact that its rotation axis is almost lying in the plane of its orbit. Long periods of sunlight follow long periods of darkness. During the winter solstice, the northern hemisphere is plunged in the night for 21 years. The planet Uranus has rings. 13 are currently known, 11 located in the inner system and 2 in the outer system. Their capacity to reflect light is extremely low. They are therefore difficult to see. These rings are composed of dust particles with dimensions of the order of a centimeter. They could have been formed by the fragmentation of a small moon after a collision with a meteorite. Uranus has so far 27 known moons. 5 of them are large. The others are only a few tens of kilometers in diameter. The largest, Titania, measures 1,580 kilometers in diameter. But the strangest of the moons encountered so far is Miranda, the 5th satellite of Uranus in size. Its surface shows complex and extraordinary geological formations. One could compare it to a giant puzzle, as if this moon had been torn apart and then put back together. It could be that Miranda was smashed during a collision, and that the pieces in orbit around Uranus were then reassembled until the moon was reconstituted. Neptune is a gas planet. Unlike Jupiter and Saturn, its solid core is larger than its total mass. Neptune's atmosphere is characterized by strong winds of over 2,000 kilometers per hour, or 1,200 miles per hour, and large cyclonic formations that persist for long periods. The most visible large dark spot is as large as the Earth. The last planet in the solar system glows with a beautiful azure color. This hue is explained by the presence of methane in its atmosphere, which absorbs red radiation and lets only blue radiation filter through. Its atmosphere is composed, in addition to methane, of hydrogen and helium. Neptune has an important internal heat source, since it emits a quantity of energy equivalent to almost 3 times that received from the Sun. 5 rings surround Neptune. They are composed of ice, covered with a large carbonaceous dust, and remain very difficult to detect. Because of its remote distance from the Sun, the number of Neptune's moons remains poorly known. Triton is the largest of Neptune's satellites known to date. This moon has canyons, craters, peaks, and very long fissures, forming a most amazing landscape. It also has very strange volcanoes on its surface. It seems that Triton's volcanoes look like geysers that emit jets of gas and dark carbon compounds from underground. Pluto was considered the 9th planet in the solar system. In 2006, it was reclassified as a dwarf planet. Dwarf planets are considered to be stars orbiting a star, more or less spherical, and often found in the vicinity of many other large objects such as asteroids, comets, or other dwarf planets. As their name indicates, these planets are small. They cannot exert the gravitational forces necessary to attract and hold objects in their orbit. With its 2,300 kilometers, or 1,430 miles in diameter, Pluto is smaller than the Moon, and yet the largest and second most massive dwarf planet. Its essentially rocky core occupies the majority of the planet's volume. Its surface consists of plains and mountains, covered with a thick layer of ice, probably water, mixed with traces of methane, nitrogen, and carbon monoxide. It takes almost 250 years for Pluto to go around the Sun. Beyond Pluto, a vast region of comets opens up. Comets are visible to us as they approach the Sun, as they develop a glowing tail. But billions of invisible comets stay at the edge of the solar system. Comets are classified into 2 families: long-period comets that circle the Sun in more than 200 years, and short-period comets. The long-period comets have orbits inclined with respect to the circulation plane of the planets. Their trajectories are varied, suggesting that they belong to a vast spherical cloud that envelops the solar system like a cocoon. The Kuiper Belt is the source of short-period comets. It is located around 30 astronomical units and extends to hundreds of astronomical units. It is home to hundreds of icy objects, some of which reach the size of large asteroids. Extending over a few tens of billions of kilometers, it is 1,000 times smaller than the Oort cloud. The Oort cloud is the reservoir of long-period comets, It extends over distances between 30,000 and 100,000 astronomical units. This spherical cloud is hypothetical, since it could not be observed directly, as it is beyond the reach of our instruments. The knowledge of its existence is based on the analysis of the orbits of several comets. In 1932, the first astronomer postulated that comets orbiting for long periods of time came from a large cloud located beyond the limits of the solar system. About 20 years later, another astronomer put forward a theory according to which meteorites could not have formed in their current orbit because of the astronomical phenomena that govern them. He deduced that they must be stored in a large cloud, the Oort cloud. A comet that passes near the Sun loses part of its mass, volatilized into gas and dust. One might think that in a few tens of thousands of years, a comet should have completely melted. However, the solar system has always been full of comets. There is, in fact, a vast reservoir of comets hibernating around the Sun. As the Sun moves through the Milky Way, it is subject to tidal forces as it passes near other stars. Comets can then be dislodged from the Oort cloud and directed towards the interior of the solar system. Comets are bodies composed of a head, which includes a nucleus surrounded by a luminous hair of gas. The nucleus of the comet presents different colorations, varying from black to gray through red. The nucleus is composed of common silicate and molecules composed of carbon, oxygen, nitrogen, and hydrogen. When it is far from the Sun, the comet is invisible, like many other small celestial bodies. As the comet approaches the inner regions of the solar system, the heat produced sublimates some of the ice present in the nucleus, which, mixed with other gases, forms the hair and the tail. As the comet passes through the solar system, the material of which the short-period comet is composed is depleted and transforms it into a tiny body among others. It happens that the Earth, during its own rotation around the Sun, crosses the dust or gases that have been left behind by a comet. These materials, while crossing our atmosphere, create magnificent swarms of meteors that are called shooting stars. During the formation of the comet's hair, carbon dioxide and carbon monoxide first evaporate. Then it is the turn of the ice. The emitted gas disperses in space and is replaced by new matter. The vaporization takes place only on the side facing the Sun, where the comet is active. The material emitted from the nucleus can spread out into space for hundreds of thousands of miles and miles. When the comet shines and becomes visible, its tail can be seen, which comes from the gases in the hair. A comet has in most cases at least two tails. One is composed of ionized gas and the other of dust. The latter are not always visible. The gas tail is bluish in color because of the presence of carbon monoxide. It can measure up to several 100 million kilometers and miles. They are always straight and consist of structure, node, and condensation. The sudden separation of the tail from its hair is one of the most spectacular phenomena. Man, from his planet Earth, seems infinitely small when placed on the scale of the solar system, and yet the universe is far from stopping there. The solar system is located in a galaxy called the Milky Way. It is a huge disk of stars in motion that measures nearly 1,000 million billion kilometers in diameter. Along its diameter, one could line up 130 million solar systems. And yet, The Milky Way is one galaxy among many. Galaxies are gigantic clusters of stars that can extend over hundreds of thousands of light years. Presenting a wide variety of sizes and shapes, galaxies are classified into two main families: elliptical and spiral galaxies. Spiral galaxies are further subdivided into simple spiral, barred spiral, and lenticular galaxies. Elliptical galaxies are the most massive. The spiral and lenticular galaxies can reach diameters similar to the large elliptical, but are less massive because they are flattened. Spiral galaxies represent 60% of all cases, and 30% are elliptical. The best known remain the spiral galaxies. Among them, we find barred spiral galaxies, which have a thick bar of stars crossing their heart and extending by an arm at each end, and normal spiral galaxies, which see their arms emerging directly from the heart of the galaxy. Spiral galaxies are flattened like a disk, with a central bulge of old red stars. The disk at the periphery contains clouds of gas and dust that will serve to form new stars. Spiral galaxies are rotating, resulting in density waves that compress the gas and dust to form bright blue stars that illuminate their arms. A spherical halo of globular clusters, containing up to 1 million old red stars, surrounds spiral galaxies. The so-called elliptical galaxies have a slightly flattened oval shape. They have 3 axes of different lengths. The lenticular galaxies have, as for them, a lens shape. They remind both spiral galaxies and elliptical galaxies. They have, like spiral galaxies, a disk with a central bulge that houses clouds of gas and dust. They differ by the absence of spiral structure. They do not have young blue stars and host only old red stars. There are 2 theories explaining how galaxies are formed. According to the first theory, galaxies form from huge clouds of gas that collapsed in on themselves by gravity. The second theory suggests that galaxies would have assembled from smaller objects. Both processes could have been at work when the galaxies formed more than 10 billion years ago. Just 1 or 2 billion years after the Big Bang, the universe then consisted of a vast expanse of hydrogen and helium. Some parts of this universe, denser than others, attracted matter, thanks to their gravitational forces. These regions individualized into huge clouds that would later become future galaxies. These different clouds were brought to meet and thus form even denser sets. During the collisions, shock waves stirred up the gas and caused it to collapse into stars and star clusters. It seems that in earlier times, the universe contained a higher proportion of spiral galaxies than today. This change in the appearance of the universe is due to repeated collisions between galaxies. Indeed, when spiral galaxies collide, they merge to give elliptical galaxies. The merger thus explains their large size and why they contain so little gas and so many red stars. From our human eyes in the night sky, the Milky Way appears as a whitish molten band crossing the celestial sphere. It takes the form of a ring, of which only a part is revealed. From the Earth, its brightness is weak and diffuse. In reality, we can only see the side of the galactic disk, composed of an endless string of stars that the human eye is unable to distinguish. Many stars, planets, and nebulae populate the Milky Way. A star is a ball of ionized gas made up primarily of hydrogen and helium, the two most abundant elements in the universe. Stars tend to collapse under their own weight. This is called gravitational contraction. The nuclear reactions that occur within the star also exert pressure from the inside out. The balance between these two forces gives stars their own dimension. The core of the star is subjected to high temperature and pressure. The hydrogen nuclei collide and form helium nuclei. Thanks to these reactions, a star can shine for billions of years. Its surface temperature will depend on its color. Our Sun is a yellow star of average size. Stars are born in molecular clouds. These are large areas of gas inside which some regions are denser than others and attract by gravity the gases present around. A globule is then formed and contracts until it becomes a protostar. The contraction causes an increase of the rotation, as well as an increase of the temperature and the pressure. The thermonuclear reactions start. The star is born. The north and south celestial poles are the extension of the Earth's axis to infinity and are the only two immobile points in the sky. The North Star indicates almost exactly the North Pole. It is not very bright, since it is only the 48th star in the sky in order of brightness, but it is one of the most important landmarks, since it does not move and always indicates north. Thanks to it, it is possible for us to orient ourselves at night from Earth without a compass or GPS. 200 billion stars populate the Milky Way, and only 3,000 of them are visible to the naked eye. The closest star system to us is Alpha Centauri. It is a complex system composed of 3 stars. The 2 largest form a double star, located 4.37 light-years from the solar system. Their size and color resemble those of the Sun. They are accompanied by Proxima Centauri. It is a tiny star, a brown dwarf, measuring 1.5 times the size of Jupiter. Proxima Centauri is a little closer to us than the main components of Alpha Centauri, since it is 4.24 light-years away. From Earth, Alpha Centauri shines with an impressive brightness. It is the 3rd brightest star in the sky. With the help of a telescope, the 2 main components of Alpha Centauri form a beautiful double star. Several types of stars populate the Milky Way: binaries, multiples, and variables. Almost half of the stars in our galaxy are binaries. Binary and multiple stars are stars that orbit a common center of gravity and are bound together by gravitational attraction. Binary stars form within the same cloud of matter, which during its collapse splits into 2 pockets. Some clouds split into multiple parts and can group up to 6 stars. A variable star sees its brightness change for several reasons. When a star passes in front of another, for example, it will modulate the amount of light we receive. The periodic pulsations of the star's surface can also change its brightness. The light emitted is a function of the surface of the star. Stars at the end of their life expand and contract. Stars can undergo unpredictable variations in brightness due to gas eruptions or other cataclysmic phenomena. Chelyabinsk is an eclipsing binary star, which is very surprising. It consists of two stars so close to each other that they exchange matter and deform each other. The larger of the two loses the equivalent of the mass of the Sun every 50,000 years. Chelyabinsk is located in the constellation of Lyra. If our planet were positioned near this infernal stellar couple, the inhabitants would see huge protuberances tear away from the larger one to wrap around the smaller one. But from the Earth, we only notice the brightness of Chelyabinsk, diminished as soon as the smaller star passes in front of the larger one. A set of neighboring stars can sometimes present a figure on the celestial sphere. These are the constellations. From the Earth, man can observe different figures drawn by stars like Orion, the Big Dipper, or the Southern Cross. The stars have their own movement, but they are so far away from us that they seem fixed. Their position will change gradually to the point that our familiar constellations will become totally unrecognizable in the distant future. The Big Dipper is the most famous constellation in the Northern Hemisphere. It is close enough to the celestial pole, where the North Star is located, that it never disappears below the horizon, whatever the time of night or the season. The 7 brightest stars of the Big Dipper form a distinctive saucepan shape. Most of its stars are less than 100 light-years away and belong to an open cluster that is almost completely dislocated. Many legends have been associated with this constellation. According to Greek mythology, it represents the nymph Callisto, changed into a bear by Hera, the wife of Zeus, after her husband fell in love with her. Zeus would then have raised the bear to the heavens to place it near the sun, Arcus, whom he had with Callisto, and who is also transformed into a little bear. The universe favoring groupings, the stars are often binary or multiple. But on a larger scale, larger groupings of stars are formed as open or globular star clusters. Globular clusters can contain from 100,000 to more than 1 million stars. They are similar to tiny elliptical galaxies. They contain old stars of red color, while the open clusters are populated by young blue stars. Within these clusters, collisions are frequent, leading to the formation of new stars called blue wanderers. Globular clusters orbit the center of the galaxy, and together form a spherical halo. The Milky Way contains nearly 150 globular clusters in its halo. One of the brightest clusters is Omega of the Centaurus. It peaks high in the southern sky in March and April. To the naked eye, it looks more like a spot than a star. Through a telescope, we can see that many small stars dot its surface. Omega Centauri contains nearly 10 million stars over 10 billion years old. It is the largest globular cluster in the galaxy. This cluster could be the remnant of a small galaxy that was swallowed by our Milky Way. Nebulae are interstellar clouds that contain the raw material to make new stars. These clouds come in a variety of sizes and colors. The smallest nebulae are called globules. Their diameter is of the order of a light year, and they look like dense and dark spots. Large molecular clouds contain enough material to make tens of millions of stars. All clouds are composed of gas and helium, as well as grains of carbon and silicon dust. When a new star forms in an interstellar cloud, the light ionizes the gases and creates luminescence. Some clouds do not emit their own light. They reflect or scatter the light of nearby stars and nebulae. The Orion Nebula is the closest to Earth. It shines according to a phenomenon of fluorescence. The atoms of the gas are stimulated by the ultraviolet radiation of bright stars, which leads them to diffuse light in turn. In this nebula, many stars and planetary disks are forming. It is easily observable from Earth simply with binoculars. This nebula looks like a small cloud in which the central region appears greenish. The Milky Way is a spiral galaxy. It consists of a flat main body in the form of a disk with a diameter of more than 100,000 light-years. This disk contains the vast majority of stars. It contains curved structures from the core that extend to the borders of the galaxy. These are the spiral arms. Inside these arms, the matter reaches a high density, and clouds of gas and interstellar dust give birth to new stars. In the center of the flattened disk, we find the galactic nucleus which shelters the halo, a shell populated by the oldest stars and globular clusters, representing the ancient stellar systems of our galaxy. Globular clusters have an extremely high density and are extraordinary objects that we can contemplate through a telescope from Earth. "27,000 light-years away from the heart of the galaxy, we find the Sun, our star. It is located on the periphery, 2/3 of the galactic radius from the center. We, the inhabitants of the Earth, travel in space, following the movements of our planet, with the whole solar system within the Milky Way. These movements are imperceptible, but they are similar to a crazy race of 600 kilometers per second, or 370 miles per second. The Milky Way rotates on itself in about 240 million years. The Sun orbits around its center at a speed of about 220 kilometers per second, or 136 miles per second. The starry sky that illuminated the Earth at the time of the dinosaurs was therefore very different from the sky we can observe today. During this time, the Sun has gone through at least 1/3 of its revolution. It moves in space with its own motion that is superimposed on the revolution around the galactic center. The stars are subject to the local attraction exerted by the nearby stars. They have their own motion and move through the galaxy. The constellations that we observe did not exist at that time, and they will not exist in the future. One of the particularities of the Milky Way and of any other spiral galaxy is that its rotation occurs in a differentiated way. The central stars and celestial objects have a shorter period of revolution than the more distant stars and objects. The objects that populate the Milky Way, such as open and globular clusters or nebulae, move across the sky. The movement of globular clusters is particularly remarkable. These dense clusters are composed of hundreds of thousands of old stars that inhabit a spherical region around the nucleus and disk of the galaxy. They are like satellites, and revolve around the galactic center in elliptical orbits more elongated and inclined than the disk. Their movement is very fast, about 200 kilometers per second, or 125 miles per second, and they regularly cross the disk. Thanks to their density, they remain stable. However, the interaction with the plane of the Milky Way leads to their disintegration. The open clusters have a different motion. Containing only a few hundred or thousands of stars, these clusters break up in the spiral arms. Their stars being less thick than those of globular clusters, they tend to disintegrate over tens of millions of years. Therefore, globular clusters can reach a lifetime of more than 10 billion years, while open clusters are younger. A large band of dust called the Great Rift splits the Milky Way in two. Originally, our galaxy was made up of stars and hydrogen clouds, and we could see through them very well. Since then, countless stellar explosions have released dust that has accumulated inside, completely changing its appearance. When we look towards the interior of the galaxy, the Great Rift is positioned between the constellation of Cygnus and the southern constellation of Centaurus. All spiral galaxies are now crossed by such dust bands. The Milky Way belongs to a group of about 60 galaxies called the Local Group. The Milky Way is not the only galaxy in the universe. Many small, faint nebulae in the night sky are also galaxies. They are distant from the Milky Way. Galaxies are not uniformly distributed in the universe. They form groups more or less large. Large galaxies are usually accompanied by dwarf satellite galaxies. There are two that can be seen with the naked eye from Earth. They appear as nebulae. They are the Magellanic Clouds. 24 other dwarf galaxies of low brightness are next to them. A little further away, we find the great galaxy of Andromeda, itself surrounded by two other, relatively large neighbors, and many small satellite galaxies. The Milky Way, accompanied by the Andromeda Galaxy and the Triangulum Galaxy, forms the Local Group with many other smaller galaxies. Counting also the dwarf galaxies, the Local Group includes more than 50 members. The three large spiral galaxies that are the Milky Way, the Andromeda Galaxy and the Triangulum Galaxy, are accompanied by dozens of smaller galaxies. The satellite galaxies are those present in greater numbers. They swarm around the large spiral galaxies like mosquitoes around a lamp. These satellite galaxies are discrete agglomerations of several million stars of a few thousand light-years in diameter. The Triangulum Galaxy has no satellite galaxies, while the Milky Way and the Andromeda Galaxy are surrounded by many. They probably grew by swallowing small satellite galaxies. This process is still going on today. For example, the Sagittarius dwarf galaxy has been stretched by the tidal forces of the Milky Way and will eventually be swallowed by it. The Large Magellanic Cloud is about 15,000 light-years in diameter. It is composed of a few billion stars and is located 163,000 light-years from Earth. Due to its high content of gas and interstellar dust, the level of star formation activity is very high. The largest star-forming region of the Large Magellanic Cloud is the Tarantula Nebula. It is so bright that if it were located at the same distance as the Orion Nebula, it would never be dark on Earth. The Large Magellanic Cloud contains dozens of globular clusters, hundreds of open stellar clusters and planetary nebulae. It contains many more heavy elements than the Milky Way. These have been created over time by nuclear fusion reactions within the stars themselves, indicating that the Magellanic Clouds are younger than the Milky Way. The brightness of the Magellanic Clouds is incomparable to that of the Milky Way. From the southern hemisphere, and in the absence of light pollution, they appear distinctly to the naked eye. The small Magellanic Cloud is located further away than its big brother, 200,000 light-years from Earth. It contains fewer stars, only 3 billion. It is less bright in the night sky, but it is still recognizable to the naked eye. The small Magellanic Cloud contains a large number of Cepheids. These are stars whose brightness varies over a period of days or weeks. The Andromeda Galaxy is located 2.5 million light-years from Earth. From the northern hemisphere, on a moonless autumn night, and on a clear day, the Andromeda Galaxy appears as a diffuse patch of light. It is one of the most distant objects in the universe that can be seen without the aid of optical instruments. The Andromeda Galaxy contains about 1 trillion stars, at least twice as many as the Milky Way. It is larger than the latter. It is the largest galaxy in the local group. However, it seems to contain fewer star-forming regions. The Andromeda Galaxy was born 5.5 billion years ago from the collision and merger of 2 smaller galaxies. The Triangle Galaxy owes its name to the constellation in which it is located. This spiral galaxy is located almost 3 million light-years from Earth. It has a low brightness. Nevertheless, under extremely favorable conditions, it is possible to see it with the naked eye from Earth. The Triangulum Galaxy is the smallest of the 3 large galaxies in the local group. It is half the size of the Milky Way, contains about 40 billion stars, and is about 50,000 light-years in diameter. The Triangulum Galaxy is home to a large number of star-forming regions, including the largest, NGC 604. This magnificent nebula in emission surpasses the brightness of Venus. Its gas is ionized by a cluster of massive stars at its heart. Distributed in at least 2 clusters, there are about 200 stars with masses ranging from 15 to 60 solar masses. The diameter of the Triangle Nebula reaches about 1,500 light-years. In about 4 billion years, the local group will see the Milky Way and the Andromeda Galaxy collide. 2 billion years later, they will merge to form a single giant elliptical galaxy. The Sun and its planets could be catapulted into space because of gravitational disturbances. The Triangulum Galaxy, meanwhile, may collide with the Milky Way a little earlier. It may end up orbiting the giant elliptical galaxy that will form during the collision between the Milky Way and the Andromeda Galaxy. Laniakea is a Hawaiian word meaning immense celestial horizon or immeasurable paradise. It is a supercluster of galaxies that includes, among others, the Virgo Supercluster, which hosts the Milky Way, and thus our planet Earth. Our local group forms with other galaxies a superstructure in a quasi-central position within the Virgo cluster. The latter is like a vast and flat expanse, including a small central bulge that is called local supercluster. The local cluster represents only one of the 6 million superclusters in the observable universe. Laniakea consists of 3 superclusters: the Virgo supercluster, of which we are a part, the Hydra Centaur supercluster, in which the Great Attractor is located, and finally, the Peacock Indian supercluster. As in most galactic clusters, the space between the different galaxies is not really empty. It is filled with rarefied gas, mainly hydrogen and helium, at a temperature of nearly 30 million degrees Celsius, or 54 million degrees Fahrenheit. Laniakea extends over 500 million light-years. This supercluster contains more than 100,000 galaxies. The mass of Laniakea is estimated at about 100 million billion times that of the Sun. Each of the 100,000 large galaxies like ours has an average of 100 billion stars and 1 million dwarf galaxies. The local group is located in the Virgo supercluster. The Hydra Centauri supercluster is the closest neighbor of the Virgo supercluster. It is actually 2 superclusters, the Hydra and the Centaur, which are gravitationally connected. The Peacock Indian supercluster contains 3 main clusters: a Bell 3656, a Bell 3698, and a Bell 3742. At the heart of the Laniakea supercluster is the Great Attractor. This gravitational anomaly in intergalactic space demonstrates the existence of a local concentration of mass equivalent to tens of thousands of times the mass of the Milky Way. Our galaxy, and all those in our supercluster, are heading towards the Great Attractor. If one imagines a picture from the sky that represents the distribution of all the superclusters in the observable universe, the Milky Way is much too small to be visualized. Proportionally, the solar system, the Earth, and man can only be imagined. We are a tiny part of a speck of dust in this vast ocean. This vast ocean in question represents, in our eyes, the so-called observable universe. The further man looks into space, the further he looks into the past. The speed of light is not infinite, but the finite speed of light, combined with the finite age of the universe, delimits an impassable border between which we cannot see. This is the cosmological horizon. Even with the best telescope, everything beyond this limit remains undetectable. Light needs time to reach us, but the possible travel time is limited since the universe is 13.8 billion years old. Thus, the light from a galaxy located 20 billion light-years away from us has not yet had enough time to reach the Earth. It is beyond our cosmological horizon. It is comparable to the horizon that sailors see from the lookout of a ship. The ocean continues just as the universe exists beyond the cosmological horizon. We just can't see it. The expansion of the universe is faster than the speed of light, which is why galaxies are far apart beyond 13.8 billion years. Telescopes do not show the world as it is, but as it was. When we look at the stars, we are in fact looking into the past. The farther we look into space, the farther into the past we see. This phenomenon gives us access to bodies or phenomena that no longer exist, such as stars that exploded in supernovae, galaxies destroyed by tidal forces, or the first years of the universe. Light has a speed of 300,000 kilometers per second. It takes time to reach us. It takes about 8 minutes for the light from the sun to reach us on Earth. When we look at the sun, it appears as it was 8 minutes earlier. When we look at the stars in the night sky, they appear to us as they were tens or even hundreds of years earlier. With the expansion of the universe, the concept of distance loses some of its meaning. When a galaxy is 10 billion light-years away, it means that it has been traveling through an expanding space for all that time before reaching us. When this light was emitted, the galaxy was at a closer distance to us than when its light reaches the Earth. Because of the expansion of the universe, astronomers are able to determine the distance to the most distant galaxies in the observable universe. The light that arrives from a galaxy brings with it a suitcase full of information about the length of its journey. The most distant star ever observed is nicknamed Icarus. This blue supergiant is located 9 billion light-years away from us. The galaxy Z8GND 5296 is one of the most distant galaxies and one of the oldest currently known. It would have formed some 700 million years after the Big Bang. Although it is 13.1 billion years old, it is actually about 30 billion light-years away from Earth due to the expansion of the universe. This galaxy appears rich in metals and would generate 100 times more new stars than our Milky Way. Although Laniakea is a most impressive superstructure, it represents only 4% of the observable universe. So what would happen if we took into account the universe as a whole? A long time ago, men thought that our planet Earth was unique. Then we discovered that there were other planets orbiting a star, the Sun. A long time ago, people thought that the Sun was unique. Then we discovered the Milky Way and its hundreds of billions of suns. A long time ago, men thought that the Milky Way was unique. Today we know that the observable universe contains 100 billion galaxies. Is it possible that humans will one day discover that there are other universes beyond the one we are able to observe? It's hard to say with any certainty how many galaxies are in the local group. Not only can't we detect all the galaxies, because some are much less luminous than others, but we still don't really know where the local group ends. What we do know today about the local group is that it is built around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. Surrounding the Milky Way are the two Magellanic Clouds and many other galaxies whose names may be familiar to you. The Big Dog, Sagittarius, Little Dipper, Dragon, Carina, Sextant, Sculptor, Furnace, Leo 1, Leo 2, and Toucan galaxies. Surrounding the Andromeda Galaxy are the galaxies M32, the Triangulum Galaxy M33, M110, NGC 147, NGC 185, and Andromeda 1, 2, 3, and 4. The Triangulum Galaxy also has a satellite galaxy, the Pisces Dwarf Galaxy. On this journey to the heart of the local group, we'll be taking a closer look at each of the main satellite galaxies of the Milky Way and Andromeda galaxies. But when we talk about satellite galaxies, we don't mean that they're completely glued to the galaxies around which they orbit. To give you an idea, The Great Dog Galaxy, the closest satellite galaxy to the Milky Way, is located 25,000 light-years from our galaxy. Apart from the two main galaxies and their satellite galaxies, the local group also includes galaxies independent of these subgroups, which we'll be observing at the end of our journey to the far reaches of the local group. We've now reached our destination. It's time to take a closer look at the local group. The local group is located at the edge of a giant supercluster of galaxies, the Virgo Supercluster. Also known as the local supercluster, the Virgo Supercluster is a supercluster of galaxies comprising the local group, and at its center, the Virgo cluster. It comprises around 10,000 galaxies, and much of its mass is probably dark matter. As the universe expands, the local group is moving away from the Virgo cluster, and therefore from the center of the Virgo supercluster. The local group extends over a diameter of around 10 million light-years. It contains every type of galaxy except giant elliptical galaxies, which are not found in such small structures. That's right, because the local group, despite its 10 million light-year diameter, is not considered a large structure by comparison with other galaxy superclusters. We can't know the exact number of galaxies in the local group. Some are too faint, others are obscured by the Milky Way. Depending on the source, you may hear talk of 60 or 80 galaxies. In any case, there are more than 50. In the local group, there are 3 spiral galaxies: the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Spiral galaxies account for 3/4 of the galaxies listed in Hubble's classification of galaxy types, developed by Edwin Hubble in 1936. Their structure is particularly complex compared to that of elliptical galaxies. Spiral galaxies consist of a flattened disk containing a few 100 billion stars and a luminous spherical central bulge known as the bulge. 2 or more luminous arms extend from the disk, spiraling around the bulge. The center of the disk rotates faster than the edges. Barred spiral galaxies like the Milky Way are distinguished from ordinary spiral galaxies. Barred spiral galaxies have a linear structure instead of 2 spiral arms. Spiral galaxies also contain a lot of gas and dust. The arms of a spiral galaxy are made up of these gases, as well as the youngest and brightest stars. Scientists believe that spiral galaxies have this spiral shape at the beginning of their lives, when they contain a lot of gas, and then gradually lose their rotation and become elliptical as galaxies merge. The local group also contains 2 Magellanic spiral galaxies, the Large Magellanic Cloud and NGC 3109. This type of spiral galaxy has only 1 spiral arm, and is smaller than an ordinary or barred spiral galaxy. Only 1 elliptical galaxy has been identified in the local group, M32, which is a satellite of the Andromeda Galaxy. Elliptical galaxies differ from spiral galaxies primarily by their elliptical shape, but not only. Unlike spiral galaxies, they don't contain a gas disk where young stars can form, and the movement of stars is random, whereas in spiral galaxies, stars are in rotation. Elliptical galaxies are made up of old stars, which is why scientists believe they form when 2 spiral galaxies collide. In the local group, M110 and NGC 147 are dwarf elliptical galaxies, a type often found in galaxy clusters, and often companions to other larger galaxies. The majority of local group galaxies are spheroidal dwarf galaxies, galaxies that are more or less spherical in shape and small in size, i.e., with a few million to a few 100 million stars. Spheroidal dwarf galaxies are ancient and have evolved very little, and their composition resembles that of globular clusters, very dense concentrations of spherical stars orbiting galaxy nuclei. Finally, the rest of the local group are irregular galaxies. These galaxies show no regular structure, being neither spherical, elliptical, nor spiral-shaped. Most irregular galaxies are dwarf galaxies, rich in bright stars and therefore very luminous. Even so, they are difficult to detect because of their small size. Scientists believe that this type of galaxy was once very common in the universe, but that collisions reduced their number. Today it is estimated that at least 10% of all galaxies are irregular. We're now going to take a closer look at each of the main galaxies identified as part of the local group, from the galaxy closest to us to the most distant. The Milky Way, our galaxy, is the second largest galaxy in the local group. It's also known as the galaxy with a capital G. It's a spiral galaxy, home to between 200 and 400 billion stars, including the Sun, and probably over 100 billion planets. The Milky Way's diameter is estimated at 100,000 to 120,000 light-years, perhaps even as much as 200,000 light-years. The center of the galaxy is a supermassive black hole, Sagittarius A, and the solar system is located 27,000 light-years from this center, so it's more on the periphery. Stars revolve around the center of the galaxy, and the Sun takes around 250 light-years to complete a full circle. Since it came into being, the Sun has made only about 20 revolutions. You may be wondering why our galaxy is called the Milky Way. When seen from the sky, the Milky Way looks like a white streak, like a milky flow of stars. In Greek mythology, the origin of the Milky Way is explained in an imaginative way. The Greeks recounted that Zeus had had an illegitimate child, Heracles, with his mistress, Alcmene. Zeus, wishing to make his son immortal, took advantage of a moment when his wife Hera was dozing to lay the infant Heracles on her breast. He begins to suckle Hera, but she wakes up and realizes that this is not her real child. So she forcefully pushes him away, leaving a trail of milk in the sky that will become the Milky Way. The Milky Way has also often been likened to a river. The Egyptians thought it was a copy of the Nile in the sky. The Chinese called it the Silver River, and the Japanese the River of Paradise. This idea of a river in the sky can be found in several Asian mythologies. Lastly, it could also have religious connotations, as was the case with the Mayans, who believed it to be a religious path, enabling souls to reach paradise. In 1610, Galileo was the first to show that the color of the band formed by the Milky Way in the sky was due to the presence of numerous stars. It wasn't until the 1920s, however, that Edwin Hubble proved that the Milky Way was just another galaxy. In the 1930s, the Milky Way's galaxy model was established, a barred spiral galaxy. The Milky Way has 6 spiral arms, which in turn divide into other spiral arms: the arm of Perseus, the arm of the ruler, the arm of the Swan, the arm of the Cross, the arm of Sagittarius, and the arm of Orion. Our solar system is located in the Orion arm. If the Milky Way appears to us as a flat disk in the sky, it's because we see it from the edge. According to researchers, our galaxy was formed by the merging of several dwarf galaxies that appeared 800,000 million years after the Big Bang, during a phase of very active star formation. There are many different types and ages of stars in our galaxy. In fact, the oldest star in the Milky Way, HE 1523-0901, is 13.2 billion years old, so it appeared shortly after the Big Bang. This is the scenario that has so far been accepted to explain the formation of the Milky Way. 13 billion years ago, two galaxies began to form stars independently of each other. On one side was a dwarf galaxy, Gaia Enceladus, and on the other, a galaxy 4 times more massive and richer in metals. 10 billion years ago, these two galaxies collided. Some of their stars were ejected into chaotic orbits, forming the Milky Way halo. For 4 billion years, violent episodes of star formation followed one another, until around 6 billion years ago. The remaining gas settled into the Milky Way's disk, which we can still observe today. Surrounding the Milky Way are orbiting dwarf galaxies, including the Small Magellanic Cloud and the Large Magellanic Cloud, which are visible to the naked eye from Earth in the southern hemisphere. The Great Dog Dwarf Galaxy is the closest known satellite galaxy to us. It is located in the Big Dog constellation, 42,000 light-years from the center of the Milky Way and 25,000 light-years from our solar system. It is an irregular dwarf galaxy and contains 1 billion stars, equivalent to 1% of the Milky Way. It was discovered rather late, in 2003, because it lies behind the plane of the Milky Way, where clouds of gas and dust are denser. However, this galaxy may no longer exist in the future. The tidal forces of the Milky Way are tearing it apart. At present, the center of the Great Dwarf Dog Galaxy is badly degraded, with a long filament of stars trailing behind it, 3 times around the Milky Way. This filament of stars is sometimes referred to as the unicorn ring, and it was this filament that enabled scientists to discover the Great Dwarf Dog Galaxy. Let's continue a little further. 80,000 light-years from Earth and 50,000 light-years from the center of the Milky Way lies the dwarf Sagittarius galaxy. This galaxy is thought to be elliptical or spheroidal, and should not be confused with the irregular Sagittarius dwarf galaxy. In fact, we don't know whether it's spherical or elliptical, as it's being stretched by the tidal forces of the Milky Way. The Sagittarius dwarf galaxy was discovered in 1994. At the time, it was the closest known galaxy to our own. It too is rather difficult to observe, as it is diametrically opposed to the solar system in relation to the center of our galaxy. Spectroscopic analyses have shown that this galaxy is probably very old. It is made up only of old metal-poor stars, known as Population 2. Scientists predict that it will eventually be absorbed by the Milky Way. A little further on, the Large Magellanic Cloud is a barred Magellanic spiral galaxy. With a diameter of 14,000 light-years, it is the 4th most massive galaxy in the group, after the Andromeda Galaxy, the Milky Way, and the Triangulum galaxy. The Magellanic spiral galaxy is a type of spiral galaxy with a single spiral arm. This type was coined for the Large Magellanic Cloud by French astronomer Gérard de Vaucouleurs when he revised Hubble's classification. Unlike the other two satellite galaxies we've seen so far, the Large Magellanic Cloud can be seen from Earth, more precisely from the southern hemisphere. In fact, it was discovered much earlier than the Great Dog and Sagittarius dwarf galaxies, since it was first mentioned in 964 by a Persian astronomer by the name of Abd al-Rahman al-Sofi. The Large Magellanic Cloud could collide with the Milky Way long before the Andromeda Galaxy. It is home to some remarkable celestial objects, including the Tarantula Nebula, a region of ionized hydrogen, or HII, and the largest nebula known to date. In this zone, the star birth rate is higher than in any other region of our galaxy. The Large Magellanic Cloud also contains stellar black holes, celestial objects created by the evolution of the most massive stars after their supernova explosion. There's also a soft gamma-ray star, SGR 0526-66, a source of gamma rays that is probably linked to young neutron stars with strong magnetic fields. The Large Magellanic Cloud is linked to the Small Magellanic Cloud by a bridge of gas and stars called the Magellanic Bridge. The Small Magellanic Cloud is an irregular galaxy located in the Toucan constellation and is one of the most distant celestial objects visible to the naked eye. However, like the Large Magellanic Cloud, with which it forms a pair, you can only see it from the southern hemisphere, far from light pollution. Like the Large Magellanic Cloud, the Small Cloud was first mentioned by navigator Amerigo Vespucci in a voyage report from 1503 to 1504, but it was Magellan's expedition that gave it its name. The Small Magellanic Cloud is thought to have been a barred spiral galaxy, distorted by the tidal forces of the Milky Way. The Bouvier dwarf galaxy lies close to both Magellanic Clouds. We are now 195,000 light-years from the Sun. This spheroidal dwarf galaxy is located in the constellation du Bouvier, hence its name, and was discovered in 2006. Its luminosity is estimated at 100,000 times that of the Sun, which is very low for a galaxy. The Bouvier dwarf galaxy is strongly disrupted by the tidal forces of the Milky Way. It is composed mainly of very old stars, aged between 13.3 and 13.4 billion years. Let's continue our journey to discover the Milky Way's satellite galaxies. Just 205,000 light-years from our solar system lies the Little Dipper dwarf galaxy, a spheroidal galaxy, located, as you may have guessed, in the Little Dipper constellation. This galaxy was discovered in 1955, thanks to a photographic survey of the night sky carried out at the Palomar Observatory, 80 kilometers north of San Diego, California. Like almost all of the Milky Way's dwarf satellite galaxies, the Little Dipper dwarf galaxy is essentially composed of old stars with little interstellar matter. A little further away, 260,000 light-years from us in the constellation of the Dragon, the dwarf Dragon galaxy was also discovered, thanks to photographic surveys by the Palomar Observatory. This spheroidal dwarf galaxy is one of the least visible satellite galaxies because it is so faint. 280,000 light-years away, the sextant dwarf galaxy is a spheroidal dwarf galaxy discovered in 1990. It too is not very luminous, and is one of the least luminous nearby galaxies. Just next door, 285,000 light-years away, the Sculptor dwarf galaxy was the first spheroidal dwarf galaxy in 1937. Analysis of its composition has revealed that it is similar to the primitive galaxies observed at the edge of the universe. Let's continue a little further afield. There are still more satellites of the Milky Way to observe. The Carina dwarf galaxy, 330,000 light-years away, is a spheroidal dwarf galaxy that formed a little more recently than the others. Most of its stars are thought to have formed 7 billion years ago, although analyses have also revealed periods of star formation as far back as 13 billion years ago, and as recently as 3 billion years ago. This galaxy was discovered in 1977 and is around 75 times smaller than our own galaxy, with a diameter of 1,600 light-years. It is moving away from the Milky Way at a speed of 230 kilometers or 140 miles per second. Recently discovered in 2018, the dwarf galaxy Antlia 2 is located 422,000 light-years from us. As you can see, its size is relatively close to that of the Large Magellanic Cloud, but its luminosity is 10,000 times fainter. In fact, it's the least luminous galaxy ever discovered. That's certainly why it was only discovered late in 2018, when most of the galaxies in the local group were already known at the end of the 20th century. The Furnace dwarf galaxy is located around 450,000 light-years from us. It is also a spheroidal dwarf galaxy, composed of ancient stars, and shines faintly. Several globular clusters have been detected, including NGC 1049, which is brighter than the galaxy itself. NGC 1049 was discovered a century before the Furnace dwarf galaxy. Let's move on a little further to observe the Lion 2 galaxy 700,000 light-years away and the Lion 1 galaxy 800,000 light-years away. Both are spheroidal dwarf galaxies. The Leo 1 galaxy is remarkable for containing very little dark matter compared with the Milky Way's other satellite galaxies. In 2021, a supermassive black hole of 3.3 million solar masses was discovered at its center. We've now arrived at the Milky Way's last satellite galaxy, the Phoenix dwarf galaxy. Scientists don't know whether this is a spheroidal dwarf galaxy or an irregular one. Perhaps that's why, when it was discovered in 1976, it was classified as a globular cluster, only to realize a year later that it was in fact a galaxy. This short tour of the Milky Way's satellite galaxies would not be complete without mentioning the Lion A galaxy, located 2.25 million light-years from us. The problem is that we don't really know whether the Lion A galaxy is a satellite of the Milky Way or belongs to the group of galaxies known as Antlia sextans. We'll be looking at this group of galaxies a little later in the trip, as it's located even further out on the periphery of the local group. Let's continue our journey towards the other galaxies of the local group. We're now 1.63 million light-years from the Milky Way, in front of Barnard's galaxy, or NGC 6822. This galaxy is a barred irregular galaxy. Simply put, it's the irregular version of a barred spiral galaxy like the Milky Way. Barnard's galaxy was so named because it was discovered in 1881 by the American astronomer Edward Emerson Barnard, who also gave his name to Barnard's star. The Barnard galaxy contains only around 10 million stars, most of them young. Edwin Hubble identified 15 variable stars in this galaxy. Variable stars are stars whose luminosity varies over shorter or longer periods of time. The Sun, on the other hand, is almost constant in brightness, varying by 0.1% over an 11-year cycle. Today, over 150 HII regions have been identified in this galaxy. Previously, it was thought that the universe stopped at 300,000 light-years. The discovery of Barnard's galaxy brought home the true size of the universe. We are now approaching the Andromeda Galaxy, the largest galaxy in the local group, with a diameter of 220,000 light-years. This spiral galaxy is also known as NGC 224, or M31, in the Messier catalog of nebulae and star clusters. This catalog, drawn up in 1774 by French astronomer Charles Messier, was intended to help comet hunters avoid confusing comets with diffuse objects such as nebulae or star clusters. The Andromeda Galaxy is located 2.55 million light-years from the Sun in the Andromeda constellation. Until the 1920s, it was thought to be a nebula rather than a galaxy. It is thought to contain around 1,000 billion stars, 2 to 5 times more than our own galaxy. Its total luminosity would be 26 billion times that of the Sun, or 25% more than our galaxy. But the Milky Way's star formation rate is 3 to 5 times higher than that of the Andromeda Galaxy, and there are twice as many supernovas in our galaxy. Perhaps one day, the Milky Way's luminosity will exceed that of the Andromeda Galaxy. Because it's so luminous, the Andromeda Galaxy is one of the few galaxies you'll be able to observe with the naked eye in the northern hemisphere. If you look carefully, you can't miss it. Its apparent diameter is 6 times the apparent diameter of the Moon from the Earth. In fact, it was discovered a long time ago. The first known written mention of this galaxy dates back to 964 by Abd al-Rahman al-Sofi in his Book of Fixed Stars. However, it wasn't until 1612 that it was observed through a telescope by the German astronomer Simon Marius, the same man who named Jupiter's 4 main satellites, the Galilean moons. The Andromeda Galaxy was first photographed in 1887 by British astronomer and pioneer of nebula photography Isaac Roberts. The Andromeda Galaxy is thought to have formed recently. For astronomers, this means less than 3 billion years ago. At the time it formed, the Earth certainly already existed. The Andromeda Galaxy is thought to be the result of the collision of 2 galaxies. Like the Milky Way, it contains a supermassive black hole at its center, called M31. In around 4.5 billion years' time, an observer on Earth will be able to see the Andromeda Galaxy in the night sky as a pinkish cloud of dust. This is because the Andromeda Galaxy and the Milky Way are about to collide. This collision will have many effects. Firstly, it will cause the collapse of the galaxy's gas clouds. Secondly, it will give rise to new stars. Some stars will be sucked into the black hole, while others will be ejected into intergalactic space. The galaxies, for their part, will merge to form a large elliptical galaxy. Their two supermassive black holes will also merge to form an even larger black hole. Around the Andromeda Galaxy, there are also satellite galaxies like those around the Milky Way. The most important of these is the Triangulum Galaxy, or M33, which is the third most massive galaxy in the local group, with a mass 60 billion times that of the Sun. It is also a spiral galaxy. Perhaps you've already heard of this galaxy, home to the fictional planet Vinea in the science fiction comic strip Yokosuno, and the planet Gliese in Jean-Gaston Van Del's futuristic trilogy. In reality, we don't really know whether the Triangulum Galaxy is a satellite of the Andromeda Galaxy, but we assume it is. The two galaxies are separated by a distance of 750,000 light-years. We are now some 3 million light-years from our solar system. Although the Triangulum Galaxy was first catalogued by Charles Messier in his catalogue as M33, it had probably been observed before. Under the right conditions, you can even observe it with the naked eye from Earth, more precisely from the southern hemisphere. In fact, mentions of this object have been found as far back as 1850. The Triangulum Galaxy is a regular, unbarred spiral galaxy, but it does have a bar running 2,600 light-years through its center. At the heart of this galaxy is not a supermassive black hole, but an HII region containing an ultra-luminous X-ray source. ULXs are still enigmatic objects for science. What we do know is that they are ultra-powerful X-ray sources. In fact, the ultra-luminous X-ray source in the Triangulum Galaxy is the most powerful X-ray source in the local group. The Triangulum Galaxy is home to other remarkable celestial objects, starting with several HII regions, the brightest of which, NGC 604, may have undergone a burst of star formation as recently as 3 million years ago. 54 globular clusters have been identified around the Triangulum Galaxy, but there are certainly more than double that number. At equal distance from the Triangulum Galaxy and the Andromeda Galaxy, 2.5 million light-years from us, you can see the Pisces Dwarf Galaxy, or LGS-3. This galaxy could be a satellite of the Andromeda Galaxy or the Triangulum Galaxy, if the latter is not a companion of the Andromeda Galaxy. This irregular dwarf galaxy was discovered in October 1978 in a search for satellite galaxies of M31 and M33. 5 objects were catalogued and grouped together under the name Local Group Suspect, hence the name LGS-3. The Pisces Dwarf Galaxy was the only one of the 5 objects to be confirmed as a local group galaxy. The Pisces Dwarf Galaxy contains old, metal-poor stars, but also atomic hydrogen gas, which may indicate the presence of young stars. It may therefore be a transitional object between a spheroidal dwarf galaxy and an irregular dwarf galaxy. What interests scientists about this small galaxy is the presence of a high-speed cloud called HVC 127-41-330. In this high-speed cloud, which is probably gravitationally interacting with the Pisces Dwarf Galaxy, no stars have been detected. and yet it has a diameter of 20,000 light-years. What's more, HVC 127-41-330 could be 80% dark matter. So, according to American astronomer Josh Simon, it could be the first dark galaxy observed in the universe. A dark galaxy is a hypothetical type of galaxy that is devoid of stars, or at least produces very few of them. If their existence is confirmed, these galaxies would be extremely difficult to detect, as they would be totally obscure. Theoretical models of galaxy formation suggest that dark galaxies are the first stage in the long process of galaxy formation. Observing one would be a giant step towards understanding the formation of our own galaxy. Although the Andromeda Galaxy's satellite galaxies, a dozen or so, are, like the Pisces dwarf galaxy, closer to us than the Andromeda Galaxy itself. Let's start with NGC 185, a spheroidal dwarf galaxy that you'll also see under the name Caldwell 18. Discovered in 1787 and recognized as a member of the local group in 1944, this galaxy is located 2.1 million light-years from us, in the constellation Cassiopeia. It appears to be gravitationally linked to NGC 147, or Caldwell 17, another spheroidal dwarf galaxy and companion of the Andromeda Galaxy. The two form a stable binary system. At the same distance from the Andromeda Galaxy as the Triangulum Galaxy is the irregular dwarf galaxy IC10. Located 2.15 million light-years from us, it belongs to the Cassiopeia constellation. Discovered as a celestial object in 1889, it was not identified as a galaxy until 1935. It was Edwin Hubble once again who hypothesized that it belonged to the local group. This was confirmed in 1966 by the measurement of its radial velocity. Smaller than the Small Magellanic Cloud, it is nevertheless as luminous as that galaxy. Its active star-forming phase lasts longer than that of the Small Magellanic Cloud, so there are several generations of stars in this galaxy. On the other hand, it is rapidly consuming its reserves of interstellar gas, which will certainly be exhausted in just a few billion years. This galaxy continues to amaze scientists, as it is also home to one of the most massive stellar black holes known, with a mass several dozen times that of the Sun. Around 2.3 million light-years away, we also find the Andromeda 2 galaxy, a spheroidal dwarf galaxy discovered in 1972, along with other galaxies named Andromeda 1, Andromeda 3, and Andromeda 4. Like the Pisces dwarf galaxy, Andromeda 2 is located between M31 and M33, so it's not clear which galaxy it's a satellite of, but scientists are leaning towards the Andromeda Galaxy. Andromeda 3, 2.5 million light-years away, is also a spheroidal dwarf galaxy. No stars are thought to be forming in this galaxy, as it contains only old stars, either the same age as those in the Milky Way, or some 3 billion years younger. On the other hand, 56 variable stars have been identified. Irregular dwarf galaxy IC 1613, located roughly between Andromeda 2 and Andromeda 3 in the Cetus constellation, has the shape of a spiral galaxy, but the characteristics of both irregular and spheroidal galaxies. It contains very little cosmic dust, making it easy for astronomers to probe its contents. On the other hand, it is very dim, so you won't be able to observe it with the naked eye. We're still 2.5 million light-years away. You can also see the Andromeda 7 galaxy, also known as the Cassiopeia spheroidal dwarf galaxy, which was discovered in 1998. This galaxy is interesting because it is the brightest and most massive of all the spheroidal dwarf galaxies that are satellites of the Andromeda galaxy. It also has the highest metallicity. Its stars are rather old, with 90% of them having formed 5 billion years ago. Not far away is M32 or NGC 221, an elliptical galaxy that is also made up mainly of old stars and has therefore not experienced a period of star formation for a long time. Scientists believe that M32 was originally a spiral galaxy that crossed the galactic disk of the Andromeda galaxy. It would then have lost most of its peripheral mass. It shows signs of a supermassive black hole at its center. Also nearby is the Whale dwarf galaxy, a low-brightness galaxy, like most spheroidal dwarf galaxies. However, it is not a satellite of the Andromeda galaxy. Indeed, this galaxy is too far away to be a satellite, so it's referred to as an isolated spheroidal dwarf galaxy. These galaxies are quite rare in the local group, but the Whale dwarf galaxy is not the only one. The Toucan dwarf galaxy, for example, is also an isolated spheroidal dwarf galaxy. Analyses carried out with the Hubble telescope have enabled scientists to establish that for 8 billion years, there has been no star formation in this galaxy. Four other satellite galaxies of the Andromeda galaxy are located further away from us than M31. These are Andromeda 1, Andromeda 5, M110, and Andromeda 6. Andromeda 1 was discovered at the same time as Andromeda 2, 3, and 4. This spheroidal dwarf galaxy is located 2.6 million light-years from us, and 150,000 light-years from the Andromeda galaxy. It is the least luminous galaxy, in which a globular cluster has been found. Andromeda 5 was discovered 25 years after the first four Andromeda galaxies. It is an unremarkable dwarf spheroidal galaxy, except for its high metallicity. M110, or NGC 205, 2.7 million light-years away, is more interesting to scientists. This elliptical galaxy contains unusual levels of molecular and ionized gas and dust. What's more, its stars follow random motions, while the galaxy itself is animated by a rotational motion. Several globular clusters have been detected in this galaxy, all of which contain old stars, except the one near the galaxy's heart. The last satellite of the Andromeda galaxy, Andromeda 6, also known as the Pegasus spheroidal dwarf galaxy, is thought to be located 3.1 million light-years from M31, and not 2.7 million light-years away, as has long been thought. It should not be confused with the irregular Pegasus dwarf galaxy, DDO 216, which is also a satellite of M31 in the Pegasus constellation. Let's go back a little further to 2.8 million light-years away, where we find the Toucan dwarf galaxy we mentioned earlier. This spheroidal dwarf galaxy is unusual in that it is neither a satellite of the Milky Way nor of the Andromeda galaxy, like the Whale dwarf galaxy. What intrigues scientists is that it lies almost opposite the other members of the local group in relation to the Milky Way. Unlike other isolated spheroidal dwarf galaxies, the Toucan galaxy is not currently undergoing a period of star formation. In fact, this galaxy appears to be gas-free. It is thought to have been star-forming for around 1 billion years, 13 billion years ago. For the last 8 billion years, no new stars have formed. In fact, the Toucan galaxy is thought to have approached the Andromeda galaxy around 11 billion years ago, ejecting it far out to its present position. Such galaxies are known as counter-current galaxies. "3 million light-years away, the Wolf-Lundmark Melot WLM galaxy is an irregular barred dwarf galaxy that is not a satellite of either the Milky Way or the Andromeda galaxy. It is located in the Whale constellation. It had already been observed in 1909 by German astronomer Max Wolf, but was not classified as a galaxy until 1926 by Swedish astronomer Knut Lundmark and British astronomer Philbert Jacques Melot, hence its name. Half of the stars in the WLM galaxy are over 9 billion years old. However, between 1 and 2.5 billion years ago, star formation resumed, particularly in the bar, so there are also young stars in this galaxy. Stars are currently forming in this galaxy. Because it lies at the edge of the local group, the Wolf-Lundmark Melot galaxy has been relatively protected from mergers and interactions with other galaxies, making it an interesting one to study. The dwarf Aquarius galaxy, also known as DDO 210, is another isolated irregular galaxy, located 3.3 million light-years from us. It is in fact part of a group of irregular galaxies that do not appear to belong to any particular subgroup. This galaxy is of interest to scientists because it shows a blue shift. The blue shift is different from the red shift, which you've probably heard of. In a nutshell, the red shift is the spectral evidence emitted by celestial objects that are moving away, such as galaxies, but also planets. Redshift is one of the evidences of the expansion of the universe. Well, the blue shift is the opposite phenomenon. The blue shift is spectral evidence that objects are moving closer to us. The Andromeda galaxy, which is approaching us and will collide with the Milky Way in a little over 4 billion years' time, shows a blue shift. The same applies to the dwarf Aquarius galaxy. It is approaching our solar system at a speed of 137 kilometers per second, or 185 miles per second. The dwarf Aquarius galaxy is one of the few local group galaxies for which we can rule out a past proximity to the Milky Way or M31. In other words, based on its current position and velocity, scientists have deduced that it has not in the past been located close to one of the two most massive galaxies in the local group. Like the Wolf-Lundmark Melot galaxy, the dwarf Aquarius galaxy still contains significant quantities of hydrogen, enabling it to support star formation, albeit at a relatively low level. The median age of stars in this galaxy is 6.8 billion years. This makes it the galaxy in the local group with the youngest median age of stars, after the Leo A galaxy. For this reason, scientists have speculated that the late star formation may be linked to the galaxy's isolation. Do you remember that we observed the Sagittarius dwarf galaxy earlier on this trip? This satellite galaxy of the Milky Way is the second closest to us, after the Big Dog galaxy. We're now looking at the irregular dwarf Sagittarius galaxy, not to be confused. The first, 80,000 light-years away, is elliptical or spheroidal. The second is irregular and lies 4.2 million light-years from us, i.e., very close to the borders of the local group. In short, one is very close to us, the other very far away. The irregular Sagittarius dwarf galaxy was discovered in 1977. As it is very close to the local group boundary, we don't really know for sure whether it belongs to this group of galaxies. In any case, if it does belong to the local group as we assume, it's the farthest local group member galaxy from its center of gravity. Far more luminous than the dwarf Aquarius galaxy we've just observed, it would have experienced a longer period of star formation and possesses a large number of intermediate-age stars. Most of the stars in this galaxy would therefore be between 4 and 8 billion years old. Just 4.2 million light-years away, another galaxy is located on the outskirts of the local group in the Big Dipper constellation, UGC 4879. This is one of the most isolated galaxies in the local group. It is an irregular dwarf galaxy. It is separated from its nearest neighbor, the Leo A galaxy, by 2.3 million light-years, the distance between the Milky Way and the Andromeda galaxy. It would seem, however, that this galaxy is getting closer to us. UGC 4879 behaves strangely, intriguing astronomers. The vast majority of its stars formed during the first 4 billion years after the Big Bang. Nothing happened for the next 9 billion years until fairly recently, when star formation resumed. In any case, analyses of this isolated galaxy have shown that it probably contains dark matter and a stellar disk. This solitary galaxy has not interacted with other galaxies, making it particularly interesting material for astronomers seeking to understand the complexity of star birth in the universe. When we were looking at the Laniakea galaxy earlier in this journey, we mentioned the Anomalies sextans group. Now that our journey is drawing to a close, it's time to take a closer look. The Anomalies sextans group is a small group of galaxies located in the Hydra, Sextans, Leo, and Pneumatic Machine constellations. On average, it lies 4.3 million light-years from us, at the very edge of the local group. For this reason, this group of galaxies is sometimes considered to be outside the local group. Many researchers say that the Anomalies sextans group is an independent group. This group of galaxies includes NGC 3109, the Sextant A and B galaxies, the Leo P galaxy, and the Pneumatic Machine dwarf galaxy. Let's start with NGC 3109. This small, barred Magellanic spiral galaxy, 24,000 light-years across, is located in the Hydra constellation, some 4.35 million light-years from us. It's a so-called low-surface brightness galaxy, meaning that seen from Earth, its brightness is less than 1 magnitude lower than that of the night sky. So far, so good. Most dwarf galaxies are low-surface brightness galaxies. NGC 3109 does, however, have some original features. It has a very low metallicity, like the small Magellanic Cloud, and contains an unusually high number of planetary nebulae for its low luminosity. A planetary nebula, which is in fact nothing like a planet, is a large cloud of gas created by a giant star at the end of its life, which becomes unstable and starts ejecting its upper layers. Planetary nebulae are magnificent celestial objects with beautiful colors. Analysis of the radial velocity of the disk deformation of galaxy NGC 3109 has shown that this galaxy and the dwarf pneumatic machine galaxy came closer together around 1 billion years ago. These two galaxies, of the Antlia Sextans group, are thought to be in a tidal gravitational interaction. The pneumatic machine dwarf galaxy is located 4.17 million light-years from us, in the constellation of the pneumatic machine, as its name suggests. It is sometimes classified as a spheroidal dwarf galaxy, sometimes as a spheroidal to irregular transitional dwarf galaxy, and sometimes as an elliptical dwarf galaxy. It contains stars of varying ages, with the youngest concentrated in the center and the oldest on the periphery. The Antlia Sextans group also includes the Sextant A galaxy, an irregular galaxy, 5,000 light-years across, with a distinctive square shape. At least it's the square shape it appears to us from Earth. The Sextant B galaxy, which forms a pair with the Sextant A galaxy, is also an irregular galaxy. It lies just outside what is considered the boundary of the local group, and is moving away from the Milky Way at a speed of 300 kilometers per second, or 186 miles per second. It is one of the smallest galaxies in which planetary nebulae have been observed. At least 5 have been identified. Finally, the Leo P galaxy is a small irregular galaxy in the constellation Leo. It is very distant, around 5.3 million light-years from us. When it was discovered in 2005, scientists thought it was a high-speed cloud. It wasn't until 2013 that its nature as a dwarf galaxy was confirmed. The Leo P galaxy is home to one of the most metal-poor environments in the local universe, with a very low metallicity, of just 3% that of the Sun, and stars containing 30 times fewer heavy elements than the Sun. In fact, the Leo P galaxy is similar to primitive galaxies. It is one of the smallest and faintest star-forming galaxies in the local group, with a total luminosity 440,000 times less than that of the Sun, and a stellar mass only 560,000 times that of the Sun, which is low. It therefore contains relatively few stars. And yet, it's one of the few galaxies in the local group, or in its immediate vicinity, if you consider that it's not part of it, that is currently still forming stars. Does that surprise you? The truth is, its star formation rate is very slow, equivalent to 1 solar mass every 20,400 years. No wonder then that it contains so few stars, even though it has been forming stars steadily for at least 4 billion years. We've now completed our tour of local group galaxies. However, it's important to remember that the local group isn't all galaxies and stars. Let's explore the local group's remarkable objects. Let's start with the Smith cloud. Does the name ring a bell? It's a high-velocity gas cloud with a mass 1 million times that of the Sun. High-speed gas clouds like the Smith cloud are of vital importance in the local group. When they fall into the disk of a galaxy, they add baryonic matter to the already diluted matter present in the disk. Baryonic matter is made up of composite particles known as baryons. More concretely, baryons are the electrons and protons that make up the atoms of all observable molecules and structures in the universe. Stars, for example, are made up of baryonic matter. You can see where we're going with this. High-speed clouds, by adding matter essential for star formation to galaxy disks, will help maintain the galaxy's star formation rate. The Smith cloud is traveling at 870,000 kilometers per hour, or 540,000 miles per hour, towards the Milky Way. It is therefore expected to collide with our galaxy in around 27 million years' time, well before the predicted collision with the Andromeda galaxy. This impact could trigger an explosion of star formation. The most recent studies of the Smith cloud suggest that it formed on the periphery of the Milky Way before being ejected some 70 million years ago. But scientists still don't know how this happened. The Magellanic Current is another notable high-speed cloud of the local group. This is the matter bridge in the wake of the large and small Magellanic Clouds. It moves at a speed of 400 kilometers per second, or 250 miles per second, well above the speed at which our galaxy is moving. We don't really know how it formed, but it's assumed that tidal forces between the Milky Way's two satellite galaxies are behind it. In 2010, it was established that it would cover a distance of 600,000 light-years, which is much longer than researchers had previously thought. From this information, scientists have deduced that the Magellanic Current may have formed around 2.5 billion years ago, when the Magellanic Clouds passed close to each other. The Magellanic Current is of interest to scientists who study it to better understand the interaction of high-speed clouds and our galaxy. Before ending this journey, let's take a look at one last unusual local group object, known as the Unicorn Ring, or Unicorn Current. We already caught a glimpse of it earlier during our exploration of the Big Dog Galaxy. This long filament of stars discovered in 2002 surrounds the Milky Way over a length of 200,000 light-years at a distance of around 53,800 light-years. We don't really know the origin of the Unicorn Ring. It could be the remnants of the merger of two galaxies, either the merger of the dwarf Great Dog Galaxy with the Milky Way, or the merger of the dwarf Sagittarius Galaxy with our own. In any case, according to a 2011 publication in the respected journal Nature, the merger of the Milky Way and the Sagittarius Dwarf Galaxy could create such rings. Another hypothesis asserts that the Unicorn Ring is not actually a ring, but simply an overdensity. Overdensities are said to be common in galaxies with distorted flaring disks, such as the Milky Way. In other words, this is not an independent structure, but a ripple in our galaxy's disk. This hypothesis was invalidated by observations made by the Anglo-Australian telescope in 2007. According to these observations, a deformed disk could not create the structure we observe. For that to happen, the disk would have to erupt, or the cause could be external to our galaxy. In short, we don't know much more at present, but scientists are continuing to investigate the origins of this original local group structure. Our journey is drawing to a close. It's tempting to explore the universe even further. you're probably wondering what lies beyond the local group. Our neighboring galactic group is the IC 342, Maffei group, which has the same structure as the local group. In other words, it's made up of two structures organized around massive galaxies. The first is IC 342, or Caldwell 5, an intermediate spiral galaxy in the Giraffe constellation, 11.4 million light-years from us. The second is actually a pair of galaxies, Maffei 1 and Maffei 2, both located in the Cassiopeia constellation. Each of these two structures has 9 known satellite galaxies. Like the local group, the IC 342 Maffei group is part of the Virgo Supercluster. The local group and the IC 342 Maffei group are only a tiny part of our universe. There are many other groups, such as Stephan's Quintet, a group of 5 galaxies located in the Pegasus constellation and remarkably photographed by the James Webb Telescope, or Robert's Quartet, a group of 4 galaxies in the Phoenix constellation. And in a few billion years' time, all this will have changed again. The dynamics of the local group itself are changing, albeit on such a large timescale that we don't realize it. With the merger of its 2 main galaxies, the local group will look decidedly different in 4 billion years' time. In place of the 2 substructures of our galaxy group, we'll have a large elliptical galaxy, whose other nearby galaxies, notably the Triangulum galaxy, will become satellites. It's also possible that the local group will one day merge with the Virgo cluster, the nearest large cluster of galaxies. But we're talking here about a future where the Earth will probably no longer exist, devoured by our sun, then transformed into a red giant. In the meantime, we have plenty of time to continue observing the local group and its surroundings, and to learn a little more every day about the universe and its formation.